Hi everyone, good afternoon and good morning wherever you are. I hope you're all doing well. Welcome to ReachSci Society Air Quality 2021 conference. We are really happy to welcome you to our event. My name is Ali Reda and I have graduated from Loughborough University with an MSc in Analytical Chemistry. I will be hosting the first half of the event, so basically the first 2 hours. First of all, I'd like to go through the updated agenda with you. So ReachSci Control, can you please share the agenda on your screen? So let's go quickly through the agenda. So currently we're in the introduction parts. Following the introduction, we'll have the welcoming message by our president. Following that, we'll start with our first keynote talk titled Airborne Particulate Matter by Professor Roy Harrison. Then we'll have a 5 minutes break and then we'll move on to the ReachSci student participants team, and that's a group presentation. And then at 3:30, we'll start our second keynote talk that is titled Air Pollution, Sustainable Solutions for Unequal Impacts by Dr. Rebecca Sari. And then we'll have another presentation by Open Seneca, and that will be at 4 o'clock. Following that, we'll have our first student presentation, that's by Mr. Abdallah Ebrir. Following that, we'll have our third and last keynote talk by Dr. Brian Caulfield, and that's titled Using Floating Bike Data to Determine Cyclist Exposure to Poor Air Quality. Then we'll have 2 more student presentations. One is by Mr. Aladdin Mansouri, and the second one is by Mr. Saeed Naili. Following that, we'll have our concluding statements by the conferencing and mentoring leader, Mr. Hussein Boumehdi, and finally, we'll have a half an hour networking session. So now we'll move on to ReachSci's founder and president, Mr. Mohammed Al-Awami, who will be welcoming you to this event and will introduce you more to what we do at ReachSci. So Mohammed, the floor is yours.
Great, thanks Ali for the introduction. I will get ahead and share my presentation. Can you see it?
Yes, we can see your presentation.
So, well, welcome everyone. Really happy to see you all here, and I hope you will have a good conference that learns at least a few stuff that will be practical to your everyday experience. Today I'll be presenting to you a little bit about what is ReachSci, what do we do, and what is the aim of this conference, and other relevant information that will be potentially useful for you to learn about us. So first of all, I'd like to thank the team who helped in establishing ReachSci. We're all PhD students in Cambridge University, and without this team, ReachSci wouldn't been established. And also, I'd like to thank all the volunteers that have joined us. We have more than 70 active volunteers now, helping us make a few new programs and also helping us in running the conferences and so on. And I would thank the amazing team in the team that organized the conference. They worked really hard, and I think they did really, really well, considering that most of them, they don't have any experience in running any conference before. So well done to you all. And I would like to thank our sponsor, the Sensor CDT. Without their funding, obviously, we wouldn't be able to run this conference or do our own program. So thank you to all of those who've been involved to make this happen. Tell you more about ReachSci. So the ReachSci started as an initiative, and now it's a society in Cambridge University. And our aim is to remove barriers in academia and research for individuals interested in STEM, so in science, technology, engineering, and math. And our vision in the next 10 years is to enable anyone, anywhere to do cutting-edge research, and hopefully we'll get closer to that goal in the next, or to that vision in the next 10 years. In terms of our program, so we have 2 different programs. The first one is mini PhD programs, and what we do basically is we design programs that give the students all the experience that they need and to do a PhD. So it's In a way, it's a mini PhD program, and we have multiple programs, we have multiple partners to run these programs. And I'll tell you a little bit more about how we run them. The second part, or the second aspect of ReachSci is to remove barriers. And what we do here is we identify barriers in the universities around the world, and we try to remove these barriers. And to give you an example, so we started a partnership with the University of Nigeria, and they have a problem with power. So they don't have constant supply of energy. And what we did there, and we also still working on it, is to try to supply them with solar power, so we can help them in getting constant energy so they can run their research normally. And this will take some time, obviously, and hopefully in the next 3 to 6 months, we'll be able to help them practically in that. So in terms of the ReachSci programs, we have multiple programs. We have the first type is specific for high school students, and we're going to run our first pilot hopefully in the next 2 months. It's going to be specific to Algeria and Iraq. The second type of our programs is specific to second-year undergrad to master students. And the first trial we run in the UK, and I think it was really successful. And today you will hear from these students to see their data. And now we're planning to run one starting next month in Angela Ruskin University. It will be in person around the same topic, so air quality. And we're planning to run an international one starting hopefully in February or March. We have also an in-depth program that's most focused on technical details and teaching students not only how to do research, but also how to fix devices and more sophisticated technical information or skills. And our first program will start in November in Ethiopia, focusing on microbiology. And we have the next one will be in Nigeria, focusing on research outcomes. So we will help them in getting solar energy, and then using the solar energy, we'll see how of an impact that made to their research. And in all of these projects, we try to give students more than 100 hours of practical experience toward a scientific achievement. In terms of the outcome, so the major thing that we hope to help the student to achieve is to master research skills, from design to collecting data, analysis, making sense of the data, and then presenting it in a good story. The second thing is obviously building confidence and helping these students build their network and prepare for their PhD. And we think this is also very key, especially the confidence part of it. We can also give them certificates to show off, and also we give them support not only through the program, but also even after the program ends. We'll continue to support them even during their flow. So from now until they get into their PhD, during their PhD, until they finish their PhD, to help them do very well across all the journey. And finally, if needed, we'll be happy to give them recommendation letter to help them get into top universities. In terms of the timeline of these programs, so they start in the first week by designing an experiment from scratch, and we give them device, they assemble this device and try to collect data with this device. In the second to third week, they collect data using this device, they optimize their experiment, and then try to collect meaningful data. In the fourth week, we teach the students how to make sense of the data, and then how to apply what they learned to make good data, to make the data analysis produce meaningful data, basically. And in the fifth to sixth week, the student learn how to make a story, how to present their data in a meaningful way, in a way that people will understand and will be engaged in their presentation. And hopefully you will notice that in the student presentation today. And in the finale, which is the conference that we're doing today, student will present their finding in a conference, and we're trying our best to make these conferences high quality so students can benefit the most from these conferences. And as I said, we also continue giving these students support even after they finish the program, throughout their career, through their PhD, and even afterwards. In terms of the outcome of the conference, so there are 4 goals that we hope to achieve through this conference. First of all, is to give our students access to high quality conferences so they can build this skill. Second, we want to help them build their network with the potential PI and employees to start helping them access opportunities. And this is, as I said, it's really, really important, is to help them build the confidence needed to present their talks. And this skill is key to becoming good scientists. And finally, as you all know, good high quality conferences accessible to very few of us, people who have a lot of money, basically. And we want to make high quality conferences accessible to anyone by making them free and by putting a lot of efforts to make them high quality. Really thank you all for listening. And if you're interested in collaborating with us, starting our program in your own university, or addressing any challenge that you have in your own university, we'll be happy to collaborate with you and work with you. And here's my information. Feel free to contact me and drop me an email, and I'll be happy to discuss that further with you. Thank you all for listening, and we'll continue to our next section.
Thank you, Mohammed, for your presentation. We hope this clarifies to many of you what ReachSci is. If you're interested in our programs, whether to attend or collaborate, please don't hesitate to get in touch. So now we will move on to our first keynote speaker. Professor Roy Harrison is He is Queen Elizabeth II Birmingham Century Professor at Professor of Environmental Health at the University of Birmingham in the United Kingdom, and also a distinguished adjunct professor at King Abdulaziz University in Saudi Arabia. His research interests are focused on air quality, especially airborne particulate matter. He is the author of almost 600 papers in the peer-reviewed literature, and he is also listed by Web of Science as a highly cited researcher. His topic is titled Airborne Particulate Matter for this conference. So welcome, Professor Roy. The floor is yours.
Well, thank you very much, Ali. I will attempt to screen share. Right, do you see that in full screen mode?
Yes, Professor Roy, yeah, we can see that.
Thank you, excellent. Right. Right, so hopefully you could also see my cursor. Well, firstly, many thanks for the invitation to speak to you today. I'm talking about airborne particulate matter because it is the pollutant causing the largest effects on human health. And I think that's in any environmental medium, so air, water, soil, and amongst the air pollutants, it's the one with the biggest public health impact. I'm just going to say a few introductory words about size distributions and chemical composition. You're an international group, so I'll show some of our international work from London, Beijing, and Delhi. We work in Beijing and Delhi because they are very polluted locations, and we collaborate with the local scientists in those cities. Talk a little bit about source apportionment of airborne particulate matter. That's to do with finding where it comes from. Then some of the latest information on emerging contributors in the UK context. A little bit about nanoparticles, which I'm sure you'll realize are very important and make up a significant proportion of the particles in the atmosphere. And then I'll take a look to the future. So airborne particles have a very wide range of sizes. They start at only 1 to 2 nanometers in diameter, and the largest are more than 100 micrometers in diameter. So that's about 5 orders of magnitude in diameter, and the properties change very much over that huge size range. We talk about, in judging health risks, we talk about PM10, which describes particles measured by mass in all sizes up to 10 micrometers. And more importantly, we talk about PM2.5, which is a fraction within PM10, just going from 0 diameter up to 2.5 micrometers. And that's the most health relevant fraction. And airborne particles have a hugely diverse chemical composition, although the major components you'll find effectively everywhere. And these are plots of particle size distributions, just to give you an idea of the sizes of particles here measured in Birmingham. I'll show you some from other locations in a moment. But the y-axis expresses the number of particles per increment in log diameter. So we have the diameters on a log scale along the x-axis. And we see that for the number, the vast majority of particles are less than 100 nanometers. So they're to the left of the plot. That means there's lots of very small particles there. But the peak in the surface area is in somewhat larger particles, somewhere about 200 nanometers typically. What we've done is we've taken the number distribution and converted it to surface area by simply using the fact that surface area is 4 pi r squared of a sphere. And if we treat them as, again, as spheres, we can multiply by 4/3 pi r cubed to convert to volume. And the volume distribution shows peaks at somewhere around 200 to 300 nanometers here. And there's a coarse particle fraction, as we call it, which here the APS is a measuring device. The SMPS similarly is a measuring device. We've got a coarse mode at probably around 3 micrometers. So if you think of an analogy with a bag of frozen peas, you might just have one bag, but when you split it open, you've got lots of very small particles inside of it. So if you were able to take a 3 micrometer particle and split it up into, say, 10 nanometer particles, which would come down here, you get a huge number of them. And so the vast number of particles are very small, but most of the mass, which is represented by the volume distribution, is in rather larger particles. So these are size distributions just in the 10 nanometer to 100 nanometer range, so just up to 1 micrometer. North Kensington, which is the blue line, is a background site in central London. Marylebone Road, the yellow, is a roadside site in central London. And we see that the road traffic is making a huge increment on that number of particles. And then sorry, this keeps jumping. I'm not quite sure why, but it must be a fault on my laptop. Delhi, for example, doesn't show such a huge number of very small particles. Sorry, I would prefer to be back on this one. In Delhi, they're somewhat larger. And sorry, that's Beijing is somewhat larger, and Delhi, they're larger again, probably because they've coagulated or they've had semi-volatile materials condensing on their surfaces. And then if we look at the diurnal pattern, so this is the total number of particles plotted as a function of time of day from midnight to midnight, we see that in the London sites, for example, Marylebone Road, it's reflecting the density of road traffic as modified to some extent by the meteorology, which affects how the particles disperse in the atmosphere. And we see rather similar patterns, except Beijing, where the peak is nearer to midday, and that's because there is a very small traffic influence here. And I'll say something about midday peaks a bit later on. They're nothing to do with road traffic. So road traffic emits lots of very small particles. And in Delhi, we see a big effect. Delhi is the red. We see a big effect of morning rush hour. And then the heavy duty vehicles, the trucks, are not allowed into Delhi during the day. They come in at night, and we see this huge peak from the diesel emissions at night in Delhi. So there's a lot of features there that tell us about local activity, which are determining the concentrations of particles. So the particle number, if we count them, it reflects mostly particles less than 100 nanometers in diameter. The surface area is mostly associated with particles of 50 to 1,000 nanometers, and the particle mass is almost all in particles of more than 100 nanometers, going up to 10 or more micrometers, and we usually measure the mass in the PM 2.5 or PM 10 size fractions. So that gives you some idea of the size of particles and some of the processes that are driving their concentrations. So the major sources, well, I mentioned road traffic, and that contains elemental carbon, which in air pollution we tend to measure by its light absorption, so we call it black carbon. And there's also organic compounds there. Particularly near the coast, there's sea salt, sodium, magnesium, and chloride. Ammonium is present as ammonium nitrate and sulfate, which form in the atmosphere from ammonia gas, largely from agriculture, nitrogen dioxide, which oxidizes to nitric acid, which then reacts with ammonia to form ammonium nitrate, sulfur dioxide, which oxidizes in the atmosphere to sulfuric acid to form ammonium sulfate. And then we have some primary organic matter, primary meaning emitted rather than formed in the air, wood smoke, cooking particles. Secondary organic matter, secondary means formed in the air from oxidation of organic vapors. And we have some dust and soil, which is major elements of silicon, aluminium, and calcium. So if we look at the PM 2.5 fraction in London, Beijing, and Delhi, the color scheme gives us the individual components. So the biggest individual component is actually, in most places, the organic matter, some of which is primary, some of which is secondary. We have a lot of nitrate, we have a lot of sulfate and ammonium, and then smaller amounts of soil and minerals up here, elemental carbon, and chloride from the sea salt. So what we see there is that all those three cities actually have relatively similar major components. It's just that the quantities, which are reflected by the size of the pies, are very different, with Delhi being the most polluted, Beijing less so, and London. And those are typical wintertime concentrations there, somewhat higher than we get in the summer or as an annual average. And then if we use what's called source apportionment to break down the London sample into its different sources, in this particular winter campaign that this data came from, the biggest chunk of the pie is ammonium nitrate, and then ammonium sulfate, sea salt moving around the pie, secondary organic from oxidation of anthropogenic, so human emitted organic compounds, secondary biogenic organic matter. So this is compounds emitted from trees, things like terpenes, which trees emit, which oxidize to form airborne particles. Road traffic, which is by no means the biggest source, although the oxides of nitrogen from the traffic contribute to the nitrate, which then goes to make the ammonium nitrate. So there's secondary traffic particles, which are in the ammonium nitrate. Food cooking, wood smoke, and just missed the last one, which is the others, which is some dust and soil, coal smoke, vegetative particles, particles from burning natural gas, and a small amount of unidentified particles. So we almost got what we call mass closure there. If we go to look at some emerging sources, things that are currently very much on the policy agenda, we have non-exhaust particles from traffic, cooking particles, wood smoke, and secondary organic particles. The easiest of these to deal with in terms of the science are the non-exhaust particles from traffic. So we tend to think of traffic through its exhaust emissions, which nowadays, as we'll see later on, are not that large. And the non-exhaust emissions are made up from brake dust, so from the disc and the pad. The disc itself degrades as well as the brake pad, forming tiny particles, tire dust, road surface abrasion, and surface dust that are resuspended by the passing traffic. And this is from the National Inventory for PM2.5, and it shows the trend in emissions from 2000 on the left to 2030 on the right. So there's some projection there into the future. We are somewhere around here, 2021, and we see that the yellow, which is the exhaust emissions, are now much smaller than the tire wear, brake wear, and road abrasion when you add them together. The inventory doesn't allow for the resuspended particles. So this is the UK national picture. So most of the particles from road traffic now are not from the engine exhaust. Moving on to cooking aerosol, there have been big advances through the development of mass spectrometric techniques for characterizing airborne particles. And these have highlighted this source of cooking aerosol. And well, I won't go into the lesser points there, which somewhat finer points, but this is believed to be a pretty significant source. And the way in which it's identified is to look at the mass spectrum of particles in the atmosphere and to then break that down into components that vary, or peaks in the mass spectrum that vary in time in the same way. And from that, there are typically 4 or more factors come out of this using a program called positive matrix factorization, which is a multivariate statistical method. And on the top left, we see oxidized organic aerosol. That's the secondary organic matter. Top right is hydrocarbon-like organic aerosol, and that is particles measured in the 3 campaigns, the repartee campaigns in Manchester. That's mostly from road traffic, and we see that big peak in the morning rush hour when the engines are cold and there are large emissions. Bottom right is solid fuel organic aerosol, mainly from burning of coal and wood, and you see the peaks are at night time, looking at that diurnal variation. And bottom left is the cooking organic aerosol, which shows the small peak at around midday or 12 to 1 o'clock lunchtime, and then the large peak when the restaurants are operating in these cities in the evening. So the diurnal variation has given that away. So cooking organic aerosol is an important source of particles. And then the next source I'd like to focus on briefly is wood smoke. And these are emission rates in grams per hour for different kinds of vehicles. So you look at the different types of passenger vehicles or heavy duty goods vehicles on the left, and the current kind of passenger car is the diesel or petrol Euro 5 or 6, which is at the top, and actually that slightly overestimates its typical emissions of particles from the exhaust. And at the very bottom there, down here, we've got a wood stove, one which is quite compliant with the old Clean Air Acts, but won't meet the new standards that are coming in after Christmas under the Eco Design Directive. But we see that the typical wood stove emits huge amounts of particles compared to a modern passenger car. And as a result of this, the UK emissions of PM2.5 from biomass burning, so from burning wood, which is given by that solid black line with the diamonds in it, and that's between 1990 and 2012, we see we've got this huge increase in emissions from biomass sources. And that's because wood burning stoves have become very popular. That won't apply to everyone's country where the climate doesn't demand it, but here they're very useful. Then the other source that we really need to pay a lot of attention to is secondary particles. And sulfates and nitrates arise, as I said earlier, from oxidation of sulfur dioxide and nitrogen dioxide, respectively, which react with ammonia from agriculture. And there's also a lot of organic aerosol deriving both from hydrocarbons from human activity and also hydrocarbons coming from trees, such as terpenes. So these things oxidize in the air and form particles. Moving quickly, and I'm very aware that time is passing on rapidly, I've mentioned nanoparticles, ultrafine particles, less than 100 nanometers. We usually measure them by number. You can measure them by mass, but the mass is very small, so it's easier to count them. And the biggest primary source in Europe is the blue there, which is international shipping. And after that, we get road transport. So that's road vehicles, mainly diesels, and that's industry next to it. So those are the big sources. And not surprisingly, if you map the emissions across Europe, you can pick out the major shipping lanes. See, this is the UK over here. You could pick out the major shipping lanes through the English Channel and so on, going up Scandinavia, and you can pick out the main traffic highways, just showing very nicely the intensity of those sources. What has happened, though, is there's been a big reduction in that transport emission, partly that's between 2005 and 2020, partly because of fitting particle filters to diesels, but also partly due to reduction in the sulfur content of motor fuel. And this slide shows how in a short period around January 2007, the number of particles at Marylebone Road, London, fell quite sharply as a result of a reduction in the sulfur content of the fuel. And that sulfur oxidizes to sulfuric acid, which makes very small nuclei on which organic compounds condense and lead to the presence of the nanoparticles in very large numbers in the air. We also get new particle formation in the air, and that is typically from oxidation of sulfur dioxide in the background atmosphere, so not immediately close to traffic, but in the background atmosphere away from traffic, and this happens in rural areas as well. You only need very tiny amounts of sulfur dioxide, which will oxidize, react with ammonia to form tiny particles, which organic compounds will condense on, and you can get huge numbers of nanoparticles, particularly in Southern Europe, where there's lots of sunshine to promote the oxidation of sulfur dioxide by photochemistry, but we don't actually know the health effects of these particles currently. Now, just briefly to wind up, a few minutes about the future. The level of black carbon emissions, and this is representative of emissions from diesels generally. We see the emissions collected on a filter from an uncontrolled exhaust on the left, going through to a well-controlled diesel particle filter on the right with intermediate stages in between. Diesel particle filters have been fitted to new cars in Europe since 2011, and we've seen a huge reduction in diesel smoke and the mass of particles from diesel exhaust. And that's seen here according to different emissions standards, which are known as Euro standards, going down on this scale to virtually zero since Euro 5 came in 2011. The component showing the greatest enhancement of concentrations on high pollution days is nitrate in both PM10 and PM2.5. And we saw the importance of that earlier on. And using numerical models, we've looked at how nitrate and sulfate respond to reductions in oxides of nitrogen and sulfur dioxide emissions. And here's a graph showing how sulfate on the y-axis responds to reductions in SO2 on the x-axis. And it's not linear. You see, that's a curvilinear plot. All means including both UK and all European sources of emissions. And what this non-linearity means is we don't get a very good bang for our buck in reducing the SO2 emissions. We get less of a sulfate reduction than we've got in SO2 emissions. So it's going to be really tough to get the levels of those secondary pollutants down. So if I just round off with some conclusions, some sources of primary emissions of particulate matter are declining. Others, like the non-exhaust emissions and the wood smoke, are increasing. Secondary pollutants dominate particle mass, are unlikely to respond linearly to precursor emissions reductions. Emissions of ultrafine particles are decreasing, but atmospheric formation is liable to increase. Airborne PM2.5 mass is declining only slowly, but many other countries have much larger problems. Just to acknowledge a few collaborators and funders who participated in this work and paid for it. And thank you all very much for your attention. I'll leave you that slide looking over Hayes on Regent's Park in London. So many thanks, and if there's time, I'm very happy to take some questions.
Thank you, Professor Roy, for your engaging presentation. We are sure that the audience have enjoyed it. So from the audience, are there any questions you would like to ask Professor Roy, or shall I ask my questions? Yeah. Sorry, I think someone has a problem with their mic. If you have any questions, could you please write them in the meeting chat?
I would like to ask one or two questions. Should I ask, through microphone or chat box?
Yeah, feel free to ask using your microphone.
Okay, thanks. So, Professor Harrison, yeah, I would like to ask two questions. The first is, the sources of the particles. I mean, what method did you use to get to the the sort apportionment of the contribution of the sources?
Yes, that's a good question. I didn't have time to go into this in the talk. We use two main methods. One is a multivariate statistical method called positive matrix factorization, which is now very widely used, which requires a large number of samples of the particles, which are analyzed in detail for their chemical composition. And then the program uses a mass conservation approach to understand the major components making up the particles. The other method is called chemical mass balance. And for the chemical mass balance method, we have to input not only the composition of the particles, but also the composition of the known sources. And the model uses a least squares approach to fit a combination of the known sources to the composition that we measure in the air using multiple chemical components. So it gets the best fit by a linear addition of different sources in different amounts to match to what we actually meet in the air. So those are the source apportionment methods that we use most commonly.
Thank you. I get it. So, is it? Am I understand this right? I mean, so you're using the PMF for source profiles, and then you use that source profile for CMB. Am I right?
No, we don't do that. It is possible to work that way around and use PMF, as I think you understand, doesn't require any input knowledge of source profiles, and it will give you source profiles, but I would not regard them as sufficiently accurate to use in a CMB model. One could do that, but they're normally independently measured by actually sampling from the sources to get the data that goes into CMB. But it would be possible to use profiles from PMF, but we don't do that.
Okay, thank you. So my last question is just that about the nanoparticles. So the results that you got was the international transport was the highest contributors. So in your opinion, do you think the event of Brexit is it had any interaction or any effect upon the contribution of international trading?
It's very possible. I don't know what changes have occurred to the volume of shipping, but any reduction in shipping would lead to a reduction in nanoparticles from that source category. But I don't know to what extent Brexit has actually impacted on that. I think it did initially, but I suspect that now things are getting almost back to normal levels of trade, in which case the changes will have been quite small. What is actually more important is that there are agreements coming through under the International Maritime Organization to reduce the sulfur content of shipping fuels in some areas, including parts of the North Sea, which will reduce nanoparticle emissions really very significantly, I believe. They certainly have a big effect on sulfur dioxide emissions.
Okay, thank you very much, and thank you for a very informative lectures. I really learned a lot. Okay, I'm going to mute now.
Thank you, Professor Roy, for answering the questions. Again, we would like to thank you for accepting our invitation to this conference and for your great presentation. We hope to see you in our coming events as well.
I want to ask another question, please.
Oh, okay, no problem.
Yeah, so which composition is more harmful and how can we reduce it?
Now that's a very good question. For the benefit of those not involved in this field, what the questioner is asking is what kind of particles are the most harmful to health? And the simple answer is we don't know. This has been looked at by the World Health Organization, by the US Environmental Protection Agency, by the UK government's advisory committee, and also the French government's advisory committee, and they all come to the conclusion that the current evidence we have tells us that airborne particles measured by mass, particularly measured as PM2.5, are harmful to health, but we can't actually pick out which types of particles cause the most effects on health. The literature is very, very inconsistent. And we simply don't have a good answer to that question. So we work with PM2.5 as the metric of particles in control policies.
Thank you for your insightful answer.
So thank you, Professor Roy, again. And dear audience, sorry about this, but due to time limitations, we need to move on to our next part. But I'm sure that Professor Roy will be happy to answer your questions if you email him. So I can see that Dr. Rebecca has joined our meeting and she's our second keynote speaker. So I would like to welcome her before we move on to our next part. So welcome, Dr. Rebecca.
Thank you, it's a pleasure.
Now for this part, we will be moving, we will not have our 5 minutes break. We'll just move on immediately to our ReachSci student presentation that was done with us in this summer. Their presentation is titled Experimental Analysis of PM2.5 Emission Derived from Different Cooking Methods and Effectiveness of Ventilation. So ReachSci team, the floor is yours.
Thank you. I will present my presentation now. Would it be okay to share my screen? Yeah?
Yes. Yeah.
All righty. Hello and welcome to our presentation. We will be presenting our data on PM2.5 emissions derived from different cooking methods and the effectiveness of ventilation. So firstly, we would like you to meet the team. So my name is Wajiha Batul. I am a third-year biomedical sciences student at Anglia Ruskin University, Cambridge.
Hello, my name is Roshan and I'm in my third year studying biomedical sciences at the University of Essex.
Hi, my name is Elizabeth. I'm a second year physics with astrophysics student at the University of York.
Hello, my name is Mafar. I recent graduate of Anglia Ruskin University studying mechanical engineering.
So this presentation, the agenda for today, we will be covering the research that we've conducted, issues that we've identified concerning chefs, and in fact, even us. We will be informing you about our background research and how we approached problems with indoor air quality, and we'll hopefully be covering our experimental design and explaining our data and hopefully suggesting protocols that can be carried out in the kitchen. So through extensive research, we found out that chefs have the least life expectancy amongst different professionals. As you can see in the chart below, chefs have an average of 8 years less than college teachers, who have the highest life expectancy of 80 years. So we decided to look into this, and we found out that there were a range of different causes. For instance, we can say that chefs work in quite confined spaces, which restrict them to sort of do exercise. They're under immense stress, which can have effects on their mental health. And also they work in hot, humid conditions. One of the main issues, though, which is the key cause of their life expectancy, is inhalation of cooking-derived fumes. So a key particle that is derived in these fumes is something known as particulate matter 2.5, in short PM 2.5. And we decided to look into this closely and study the implications it has on the health. As you may notice, butlers, waiters, and cleaning personnel also have quite low life expectancy. And we believe this is the same reason, since the environmental conditions for these are similar. So you may be wondering what PM 2.5 is, and we'll be going through it right now.
Alrighty, so PM 2.5 is defined as particulate matter of aerodynamic diameter of 2.5 micrometers or less. This is a good illustration of the size of PM 2.5 in comparison to the human hair. As you can see, PM 2.5 is a very fine particle, around 20 times smaller than the width of a human hair. This kind of consists of combustion particles, organic compounds, and metals. And due to its small size, it has an increased penetration potency in the lungs, which does make it quite important in studying disease and its mechanisms. So here we have a good proposed mechanism as to how PM can affect certain health conditions. Prior to that, we will look into why PM 2.5 is so detrimental to health. So PM 2.5 is a constituent of cooking fumes, which are produced when cooking is done at high temperatures. Also, when oil is degraded and proteins are pyrolyzed, so broken down thermally. And these are the main reasons as to why cooking fumes do arise. So most of the PM 2.5 derived from cooking oil fumes do contain potentially carcinogenic chemicals such as polycyclic aromatic hydrocarbons. These are known in short as PAHs. These, as illustrated in the figure, can be a constituent of both PM 2.5 and PM10, but again, in our research, we did look in depth into PM 2.5. So here in the schematic, we can see that PAHs can interfere in many cell signaling pathways. They can induce apoptosis and epithelium damage due to the fact that they cause inflammation when inhaled in the lungs. The oxidative stress can also cause damage in DNA, which can cause mutagenicity, and this can manifest into various forms of cancers, in particular respiratory cancers, cancers of the lung. However, epithelium damage can also cause a variety of cardiovascular diseases.
From the title of the slide, we see that the upper limit of exposure, or rather the moderate exposure level of any human being over a period of 24 hours is 35.4 micrograms per cubic meter. And we also see that the table below is Inequality Index table, which shows the category and the index values, as well as the breakpoints. This table is used by various organizations, government arms, even private sectors, in a way to inform people of the important information that they need to know, of how much they can be exposed to, especially those with cardiovascular diseases. I'm sure everyone here has a smartphone and with a weather app, and due to recent updates, we see that the weather apps now shows an air quality index of the area we're in, as well as the category. So this is also another way that this chart or this information is used to inform people of what they can and cannot be exposed to at any given time. Right, so the device that we're using this experiment was provided by OpenSeneca. It's battery powered, which is also rechargeable. Also the micro SD memory card to store the data, which is collected throughout the duration of the experiment. It basically shows us all the different variants that we'll be monitoring during the experiment.
So we broke our experiment down into 3 points, and our aim of this was to identify methods for mitigating unhealthy levels of PM 2.5 that arise from cooking beef using 3 different cooking methods, namely microwave, oven, and frying. So as you can see, we used the 3 different methods. There was a 1-hour pre-ventilation between each experiment, and PM 2.5 levels were monitored over a 2-hour period during and after cooking. Beef measurements were kept constant as we used a 100-gram, 8-centimeter round with 1 centimeter thickness. So experiment 1 was frying beef with a ventilated versus a non-ventilated system. So that was with windows and doors shut and then windows open. This was to see if ventilation has an effect on concentrations of PM 2.5. And then experiment 2, we used an oven where the first experiment, we kept the door closed throughout data collection. And the second experiment, we opened the door after the beef was done cooking. This was the same with the microwave. And we chose to do this to see if the seals on the microwave and oven have any effect on preventing PM 2.5 being emitted into the kitchen.
So below you can see the different kitchen layouts that were performed, where the experiments were performed in. These varied in their parameters and areas. So on the far left, you can see one of the kitchens, which had roughly an area of 8 meters squared, the middle with an area of 17, far right with an area of around 5, and at the bottom with an area of about 12. So we discussed that maybe different sort of sized kitchens may sort of have an effect on PM 2.5 levels. For instance, larger aread kitchens might mean that PM 2.5 particles may be more distributed into the environment, and also this may mean that there may be less exposure to PM 2.5 and therefore reduction in the tears that sort of are produced whilst cooking. And this goes the same with smaller kitchens where people may be exposed to more PM 2.5. So the baseline levels were carried out as our negative controls. They were carried out in 3 different conditions. So for the kitchen, we ventilated for 1 hour and we left the device monitoring those levels. As you can see, they average at quite low levels between 2 and 4 micrograms per meter cubed. The oven, on the other hand, does have a larger range where it sort of ranges between 8 to 12 micrograms per meter cubed. And this was performed by preheating the oven to about 180 degrees Celsius for about 15 minutes. And on the microwave, on the other hand, the range was sort of similar to that observed in the kitchen baseline levels. They're between about 2 to 3 micrograms per meter cubed. And all of these, as you can see, are sort of steady and they have a little bit of fluctuations. We sort of discussed why oven may have had initial sort of high PM 2.5 levels. And we did, according to some literature search, we found out that this may be because of something called pilot lights inside the oven, which is something that's continuously run, serves as a thermostat. And so when ovens are on, this can allow the ovens to ignite.
All right, so for our positive control, we obtained data from frying beef without ventilation. As previously mentioned, we chose to do this because the greatest levels of PM2.5 could be obtained from cooking at high levels, high heat levels, also from the degradation of oil and the pyrolysis of proteins. So we combined the three of these to use as our positive control and obtain the highest values. As you can see here, we obtained the values of 500 micrograms per meters cubed, and these stayed at the very high levels for a long time in a non-ventilated system.
So our first experiment was frying beef. How we did this was on the device, we preheated 2 tablespoons of vegetable oil for about 2 minutes. And after we placed the beef patty, which was prepared in the same sort of way Elizabeth mentioned before, we heated this until the temperature sort of reached about 72 degrees Celsius. And we used a thermometer to sort of monitor this. And again, the flame was on a medium flame. This experiment was carried out in 2 different conditions. So one was without ventilation. This meant that windows and doors were closed, as well as extractor fans. And on the other hand, we had the second environment where ventilation was in place and windows and doors were left open.
So here we have the results from experiment 1. So on the left-hand side, you can see our results from frying beef with ventilation. So the windows were open in this case. The PM levels steadily increased over a period of 15 minutes and hit a peak at 250 micrograms per meters cubed. And then they steadily decreased back to baseline levels as the PM goes from an area of high concentration to an area of lower concentration, which is outside in this case. The peak is at 250. It's quite useful to note that. The orange line here indicates the healthy levels according to the air quality index. This was around 35.4 micrograms per meters cubed. Now, we know that these levels are exceeded when frying with ventilation. However, they do come back to baseline levels pretty quickly. So ventilation has definitely been effective in this case. Now, on the right-hand side, we can see PM2.5 levels when frying beef without ventilation. Here, the PM2.5 levels increase to 500 micrograms per meters cubed. This is twice as much as with ventilation. So very unhealthy levels. And then they decrease to 300 and do not drop lower over the period of 2 hours in which we collected the data. Again, you can see the healthy levels of PM2.5 over the period of 24 hours that is recommended by the AQI. And again, the levels that we reached throughout this experiment is 10 times higher than the recommended amount. And they do stay at those levels for a prolonged period of time. So the exposure rate is a lot more. So the health implications for those that work in kitchens with bad ventilation are quite high. It is quite useful to note that during this experiment, I personally did experience tears whilst cooking, which is an irritation in the eyes whilst cooking. And this is a good, the prevalence of TWC, tears whilst cooking, it provides a good indication of groups that are at greatest risk of health implications. So it is quite useful to note the effectiveness of ventilation throughout this experiment.
So for the second part of this experiment, we looked at oven cooking. So you can see the setup here. 100 grams of beef was placed in an oven-proof tray after 15 minutes of preheat. It was cooked for either 30 minutes or 15 minutes in a gas or electric oven. This is a limitation of our study, as not all ovens are the same and will be discussed later. The cooking temperature was kept constant at 180 degrees C. And this was done with the oven door kept closed after cooking, and then again with the oven door opened immediately after cooking.
On the graph below, we see there was an anomaly in the results that were produced by cooking using the oven. So if you look at the graph on the right, where the door was closed after the experiment was finished, we see that there was a peak in the results, which reached a peak of 15 micrograms per cubic meter, which is way over or way above the results that were shown for when the door was opened after the experiment. This could have been caused by a device malfunction or inadequate ventilation of the room before the experiment started. Yes, which mean that there's an increased amount of PM2.5 present in the room at the time of the experiment. Right, to introduce the third experiment that we conducted using the microwave. By default, the running time for the microwave was 5 minutes. The microwave was set at default settings, basically factory settings, using the same 100-gram beef meat sample. So it was conducted in 2 stages. The first one being the microwave door being left closed after 5 minutes running time, and the second one, the door was left open after the 5-minute running time.
So here are our results from the microwave experiment. On the left-hand side, you can see we cooked the beef in the microwave for 5 minutes, left the reading on for the period of 2 hours. However, we kept the microwave door closed throughout our readings. Here you can observe the peak at 5 micrograms per meters cubed within the 5 minutes. We've labeled this the 5-minute microwave peak, but I will detail that a little later. On the right-hand side, you can see that the levels of PM2.5 rise much higher. So the peak is at around 65 micrograms per meters cubed. This exceeds the healthy levels, unlike the previous when the door is closed. And then this reduces back down to baseline levels. I have added a zoom in just to see where the levels do come back down to baseline, and this is at around 3 to 4 micrograms per meters cubed. It is quite interesting to see that the peak is much higher when the door is open as compared to when the door is closed. This just goes to show that the microwave seal is very effective in minimizing the outflow of PM2.5 from the cooking into the surrounding atmosphere. So it's recommended, we recommend that after cooking in the microwave, it's best to keep the door closed for a few minutes after cooking and then proceed with taking the food out.
So we found that using different packets of meat, despite the same brand and the same fat content, produces variable results. As you can see, the second meat produced a much higher peak, peaking around 30 compared to the first 2 runs, which were completed using the same packet of meat. It was also observed that the second meat spat more violently when in the microwave, and this could be another example of how the meat varies between packets, and therefore that further research is needed into different packets and types of meats to see if the microwave is truly the best in producing the smallest amount of PM2.5.
So we experienced many different limitations in the experiment. Elizabeth, if you'd like to go through them again.
Yep. So we also found that the oven produces varying results. As you can see, the red line, which has an arrow towards it, was a very high baseline, which was when the oven was run with nothing inside of it. It was observed that something burnt during this, something that was left over from previous use, which is a limitation of the study because we were using family ovens that are used every day, well, almost every day. with different foods being cooked. So the oven is never in the same state that you would leave it. And therefore, if we were to do this experiment again, we would use an oven that is used simply for this experiment and is clean between runs.
Another limitation that we experienced were flaws with the device. For instance, the device seemed to be recording quite abnormal levels of PM2.5. As you can see below, we have different runs performed by one of us. As you can see on the far left, you'll see that the highest PM2.5 values range sort of about 300 to 4,000, 3,000 to 4,000 micrograms per meter cubed. In the middle, you can see it reaches nearly 12,000. And on the far right, you can see it reaches nearly 1,800. We looked into the data and we did see quite a large range between the PM2.5 values that were recorded by the device. For instance, the lowest values were sort of recorded sort of like 0.125 micrograms per meter cubed, and the highest was about 12,000. So this did suggest that there must have been some sort of malfunctioning in the device. As you can see, we have a little bit of a subsection of the AQI below, which shows that the most hazardous range of values range about 350.5 to 500. And clearly, as you can see, these are far off the results that we've got. So we may need to be repeating some experiments in order to gain more accurate results. Another limitation that we experienced was with time flaws. So as you can see on the left, this was one of the graphs that were initially constructed. They sort of demonstrate gaps throughout the entire course that the device was recording. I looked closely into the raw data and I found that there were really huge jumps from one time to another. As you can see on the far right, 55,959 jumped straight to 60,000. And as you can see beneath that, you can see that straight from zero, it jumps to 10,746, which is just sort of an indication that there was some malfunctioning. How we did sort of combat this was we renumbered the times from 0 milliseconds to in 1 millisecond intervals. And when we did that, we produced the graph on the right. And as you can see, this did show a steady trend where the baseline was sort of at around 5 micrograms per meter cubed, as shown earlier.
The other limitation that was there when we conducted the experiment was the difference in the kitchen layouts. The difference in the area of these kitchens played a vital role in the behavior of the pattern of the PM2.5 distribution in each room. Another thing that also was a contributing factor was in each kitchen, there are different arrangements, appliances, commodities, as well as ventilation as well. Some kitchens were ventilated, some are not. In turn, this presents varying data, and hence we can see the difference in the results that have been presented thus far.
So to conclude, we identified a problem, which was a reduction in lifespan for chefs. We attributed this reduction in lifespan to their exposure to PM2.5 particles. And then we decided to look into a common cooking method, which is the frying of beef, in particular because of the fume emissions that are derived from this method. And then we looked into the different methods of cooking to mitigate these effects. From our data, we can see that ventilation has been very useful in minimizing the production of PM2.5 during frying, and the really hazardous levels at which non-ventilation can keep the PM2.5 levels at. The microwave door was effective in containing the PM2.5, but the oven doors weren't. It is useful to keep into account that this experiment needed to have been repeated, as we aren't sure whether the oven doors were in fact efficient or not, due to the initial levels of PM2.5 that were quite higher than in one experiment than the other. PM 2.5 levels exceeded 35.4 micrograms per meters cubed in several cases, but again, we could mitigate that with keeping the microwave doors closed, the oven doors closed, and getting a good ventilation system throughout our cooking. Chefs are constantly exposed to hazardous levels, and the best way in which we can mitigate these effects is will be highlighted later on.
So we've just discussed what restaurateurs can consider in terms of health and the levels of PM 2.5 being produced, but restaurants may want to consider other factors such as the texture of the meat. For instance, microwaves, although produce the least amount of PM 2.5, they produce very dense and shrunk meat, which will be shown in a bit. Cheaper cooking methods, if they want to be considered, gas is a good alternative, so the stove can be preferred over the microwave and oven. However, although this does have initial low costs, long-term costs such as maintenance and running costs and installation may need to be considered, as this can sort of up the price a bit. Microwaves, apart from the benefit of sort of producing least PM 2.5 levels, also are able to be run with very less energy compared to the other methods, as well as working very fast, which maybe restaurants do need if lots of customers are coming in.
During our experiment, we found that frying beef produced the best textured meat consistently and was the easiest to achieve compared to other methods. So meat in a microwave, as said before, produces a dense, shrunk meat, which isn't very desirable for customers, and therefore a restaurant wouldn't want to produce this. Meat in the oven and microwave, and these results were equally dark, perhaps suggesting that we got the timings wrong and we've overcooked the meat, and therefore it would be useful for restaurants to look into different timings and find the best timing that would produce a nice piece of meat that they could sell to customers, which would also reduce the PM 2.5 that their chefs are exposed to.
So to protect the health of chefs and perhaps protect you in your own kitchens, we have provided some sort of recommendations for you to protect yourself against PM 2.5. For instance, whilst cooking, chefs can wear something called PM 2.5 carbon masks, or they can use charcoal filter splatter screens, which allow the PM 2.5 particles to be avoided in inhalation. Extractor fans, doors and windows, as well as air purifiers can be incorporated more into kitchens. And through reading, we found out that boiling water and vinegar, or alternatively cooking baking soda nearby, can allow PM 2.5 to sort of be absorbed, hence reducing its concentration in the atmosphere. Although these are the factors that can be controlled whilst cooking, there were other factors that can be controlled inside the chef's kitchen. For instance, smoking can be avoided, since cigarette smoke can be a source of PM 2.5. Cleaning products often sort of comprise carcinogens, which are some of the key causes for cancer, such as the lung cancer. Restaurants often tend to sort of burn candles as well, and that is a source. If molds in kitchen can also be sources of PM 2.5, which may mean that restaurateurs may need to sort of handle that in appropriate manner. Volatile organic compounds also, which are sort of in paint, carpeting and upholstery materials, can sort of be managed. For instance, controlling the aerosol products that you use, such as air purifiers. And instead of using solvent-based paints, they can opt for water-based paints instead. Wafar, I think you're on mute.
Oh, sorry. I'm looking at other, looking at air quality in general. There are other factors that can affect the air quality outside the kitchen. Of course, an example, we have livestock rearing and breeding. we all know that livestock produces solid waste, and solid waste is a direct contributing factor to greenhouse gases, which in turn cause global warming. As well, we know that livestock as well is fed. A lot of cattle and other livestock are grass-fed, and this also causes a destruction in the ecosystem, in turn reducing the ability of the ecosystem to neutralize greenhouse gases that are excreted into the atmosphere. And we also have, as a direct effect or direct activity of livestock rearing and breeding, eventually after the cattle or after the livestock has been slaughtered and is transported to markets, which is also another additional factor of greenhouse gases into the atmosphere, causing global warming as well as other greenhouse related issues.
Yep. Future work that we could suggest is investigation of PM 2.5 in industry. So these experiments can be carried out in restaurants to monitor the levels of PM 2.5 over a period of 24 hours to be compared with the AQI levels and see how much they exceed. And then proper suggestions could be put into place to minimize the levels of PM 2.5 to ensure that chefs are working in safe environments with the correct containment levels in place. We could investigate using different air pollution monitors. So with the Open Seneca air pollution monitor, it was compact and easy to use, which was great. However, we did face many issues with the battery life, of course, as we had 6 different experiments that were carried on for 2 hours each, sometimes with, interrupted runs. So charging time did take quite a while too. That was one drawback. So it would be interesting to use different air pollution monitors and perhaps look at different aspects of PM 2.5 as well. Levels of PM 2.5 could be recorded in surrounding environments. So we conducted the experiments within our kitchens. It would be interesting to see if any of the PM 2.5 leaked to surrounding rooms or living areas and see how high the levels are there, if they're still within the range, still within safe levels or not. Similarly, within restaurants, we could repeat this as well. Not also looking at just the kitchens themselves, but also the area in which the dining takes place, just to see how much pollution people are exposed to, and compare the average time an individual spends in a restaurant, perhaps different restaurants too, and see their risk of exposure to these particulate matter 2.5. Experiments should be repeated to test for reliability within results. As you may all be aware, we are all students conducting these experiments. We had to conduct this over a period of 4 to 5 weeks, during which time we did have some exams to do as well. And so the time we had was quite limited. And again, as I mentioned, we had 6 experiments, 2 hours each, some of which were faulty. So runs had to be repeated and getting the data was quite difficult. So in future, we could repeat these experiments just to test the reliability and gain solid conclusions. We would like to thank Sensor CGT, Open Seneca, and ReachSci for this collaboration and working with us to give us a good insight into the PhD experience. We're free to take any questions and we'd like to thank you for your time.
So thank you, ReachSci students, for your wonderful presentation. You have worked very hard in the project and have successfully completed it. Good job, everyone.
Thank you.
You're welcome. So in the participants, I can see that Professor Royshan has joined us. So I would like to welcome her and I would like also to thank her for all her support in in the ReachSci program.
Thanks very much. I don't know if you can see me now. Hopefully you can. I can see that you have done a tremendous amount of work, and congratulations to you and to your mentors for this. So very, very nice work. I do have a question, and it struck me right at the beginning and then again at the end. It's about the lifespan of the chefs. It did occur to me that maybe there were other factors, and I wondered if you'd considered that maybe people who work in kitchens, they tend to have lower salaries. Maybe that means then, you know, of different socioeconomic class, that might mean that they have less access to healthcare and so on. So, you know, just being careful about that correlation and causation thing. So I just wondered if you thought about that.
We did consider this actually, and we did carry out literature search, and we did find out that the main cause of their life expectancy, decreased life expectancy, is because of the work that they do in kitchens. We did touch on mental health, for instance, like the stress that they may undergo in kitchens due to how hectic and how fast-paced it must be. So yeah, I think maybe we could look into depth next time, hopefully.
Yeah, sounds good. Thank you.
It's okay.
So I can see that Professor Roy would like to ask you a question.
Yeah, thank you. Very interesting talk. Nice piece of experimental work. I'm a little bit puzzled by your air quality index, but I won't go into that. I'm not a big fan of air quality indices because they're not all constructed in the same way. So I don't think you can combine them. But my question regards the monitoring device that you used and how that was calibrated.
This device that we used from OpenSeneca did come pre-calibrated. However, before each of our experiments, we did wait a minute or so for the baseline levels or initial readings to stabilize. But yes, these devices do come pre-calibrated.
Do you believe the calibration?
In some experiments, there were quite a few faults that we found. For example, the gaps within the timings. So it's quite a difficult one to define, to be honest with you.
Well, it's always good to be very critical about these things. So I wouldn't personally want to do experiments with uncalibrated instruments, and a manufacturer's calibration, we know on a lot of these lower cost sensors is probably okay for the first week of use, but after that it can drift and it can be very incorrect. But I'll leave it there. I won't labor the point.
Lorena has a question.
Hi, thank you. Thank you for all the work. I just wanted to mention, so I'm from the OpenSeneca team. I'm giving a presentation later on, so I'll mention regarding the calibration point. And I think that's actually a point that I wanted to ask if you've noticed, or you would need to have more data, that the sensor behavior changed after the experiments, in the sense that, you know, you expose them to such high levels of particles. If you've noticed after that, they kind of started working or becoming more faulty or not working properly.
I actually sort of figured out that with my device in particular, since I started recording all my experiments, I experienced the same sort of pattern. So I'm assuming there must have been some sort of constant fault. But weirdly enough, to expand on your point, yes, when I was actually carrying out my negative controls, they were at quite steady and low sort of expected levels. For instance, my negative control was around 5 micrograms per meter cubed. So yeah, that might mean that with high concentrations, it might sort of, device might sort of play up, I guess.
You mean that the baseline was too low or too high?
The baselines were expected, yeah, they were expected, okay. Yeah.
Okay, thanks.
Thank you.
So anyone would like to ask a question? Dr. Rebecca, would you like to ask them a question or give them a feedback?
Sure, I'd be happy to. I just want to second that I think that was an excellent presentation, very well organized, a lot of hard work, and some clear, actionable results. So I'm going to make sure my microwave's closed when I'm done cooking. And so thanks very much for your hard work. I hope it was a good introduction to some of PhD life and has whet your appetite for more.
For sure. Thank you very much.
So anyone else would like to ask any questions before we move on to our next presentation? Yes, Mr. Zahir, you would like to ask a question?
Hi. So first of all, it was a really sort of a good presentation and really enjoyed it, looking into it, the kind of emission you can get doing the different cooking. Looking at the emission profile, there was just one thing in my mind that came up. You might have told anyway, because the scenario was, let's say, the good ventilation or poor ventilation. So when you guys were cooking, the ventilation was only through window, or you also had some extracted? Because quite often in the kitchens, when we have the extraction fan functioning, that plays a major role in providing you the ventilation. And quite often, practically speaking, for a residential sort of microenvironment, the use of functional extracted fan is quite good. So was there such a sort of extractor fan in your kitchens as well, or you didn't look into it?
Yeah, so we found that for some of our kitchens, the extractor fans were there, and for others, there weren't. So in order to keep things, controlled and the same in each experiment, in each of our runs, we decided just to open the windows. Because there were windows in each kitchen. Sometimes there weren't doors, sometimes there weren't extractor fans. So we decided on just the windows.
Okay, good. That was good. Thanks.
Thank you.
So anyone else would like to ask a question? So thank you again, ReachSci students, for your efforts, and we wish you all the best in your coming projects. Now we'll have a short break for 5 minutes, and we will continue after that with our second keynote speaker, Dr. Rebecca, after in 5 minutes.
All right, thank you.
Thank you. So again, welcome everyone. We're back, this time with our second keynote speaker, Dr. Rebecca Sari. She's an assistant professor in the Department of Civil and Environmental Engineering at the University of Waterloo in Canada. Dr. Sari studies the consequences of climate change and climate policy on human health and environmental inequality. Dr. Sari is also an internationally recognized expert in quantifying the health and economic impacts of air pollution under climate change. Her topic for today's talk is titled Air Pollution, Sustainable Solutions for Unequal Impacts. So welcome, Dr. Sari, again, and the floor is yours.
Wonderful, thank you. Let me just share my slides here. Okay, good, can you see them?
Yes, we can see that. Thank you.
Excellent. Okay, I'll get started then. Thank you so much, first of all, for the invitation to speak to you today here at the ReachSci Air Quality Conference. I think the mission of ReachSci is really commendable, and I hope it's been a useful and inspiring experience for everyone who's participated so far, and I'm happy to be a part of it. Thank you for your interest in this topic of air pollution, which can have significant impacts for our health, and those impacts can be very unequally distributed, which is what I'm going to talk about today. As we've been hearing about, air pollution is harmful for our health. In fact, it's one of the most harmful risk factors out there that contributes to global premature death. Here we see a ranking of all of the risk factors contributing to premature death worldwide from the Global Burden of Disease study. And at the top, we see a lot of the usual suspects: high blood pressure, smoking, high fasting, high blood sugar, high body mass index, high cholesterol, all of which might not be too great for the chefs that we heard about in the students group, by the way, if they're eating lots of rich, sugary foods and smoking on their breaks, for example. But the first environmental factor is outdoor particulate matter, then alcohol use, and then household air pollution, so that indoor air that the student group studied. And then down the way, the next air pollutant that's of interest is ozone. Now, these pollutants are associated with a variety of different types of illnesses those illnesses that cause death. These include lower respiratory infections, lung cancer, cardiovascular disease, heart attacks, chronic respiratory disease, including asthma. And those health effects have associated economic impacts as well. So for example, lost school time, lost work time, lower productivity, higher healthcare costs. And all of this adds up in Canada, where I'm speaking to you from, to the tune of about $50 billion in economic damages each year due to air pollution. Now in Canada, we're lucky to enjoy relatively clean air, and that is not the case in most of the world. Most of the world lives in what's considered to be polluted air, exceeding the World Health Organization guideline. And we can see that here with this mapping of which fraction of the population is exposed to levels at least as high as a given concentration, with the World Health Organization standard here at 10 micrograms per cubic meter. And we can see, for example, I'm here in North America, high income, in bright green, and most of us are exposed to levels that are below the standard. However, for most of the world, that's not the case, and especially for some of the lower income regions like Middle East, North Africa, East Asia, and Southeast Asia, such that over 93% of those pollution-related deaths occur in low-income regions. In my lab, we aim to do research that helps us to better understand and solve this issue. So we like to ask, How bad is the problem, and what can we do about it? What are the solutions? What will they cost? And what benefits will we gain in terms of protecting our human health and the most vulnerable among us? And the good news I have for you is that those benefits are quite large and often larger than we think. In this talk, I'm going to present work on disparity or inequality in health impacts due to fine particulate matter and ozone. I was invited to focus on our work that explores some of the current inequalities in human health due to pollution in China. So that will be the main focus of my talk. However, in my work, I'd like to focus a lot on solutions and ways we can make things better. So in any remaining time, I'll briefly touch on some of our policy analysis work to give you a flavor of PhD work in that area. I'm going to start by reminding us that size matters when it comes to particulate matter exposure. And we've heard some discussion of this already in previous talks, including our student group, and our first keynote speaker emphasized some of the issues with nanoparticles, which would be particulate matter that has aerodynamic diameter in nanometers, so less than 1 micron. And these are all, often called ultrafine particles. And the reason we get more and more concerned with smaller particles is that as we've been able to study smaller and smaller particles, we've often found that most of the health impacts are coming from the finer and finer range, because as we've already heard, they can penetrate farther into our body to cause more systemic issues. The issue, however, even though we are having some good evidence about different health issues with smaller particles from smaller scale exposure studies or from particle cell lab studies, we don't have the scale of ground level monitoring, for example, in the smaller particle sizes that we do now for PM2.5. And what this means is that our understanding of population scale exposure to smaller particles is limited. One way that we can get data over a large area without deploying a lot of sensors on the ground is to look from space. The atmosphere is essentially a very thin layer between outer space and the Earth's surface. And so examining the way that it affects light that travels through it, we can get a sense of what's inside it. And my former PhD student, Dr. Ming Liu, developed a method to combine satellite optical products with properties of particles in the air to estimate concentrations of particulate matter at the ground and sort it by particle size. We use this to look at exposure to fine particulate matter based on size in China in 2017. On the figure in the left, you can see the mean effective particle radius, so the size of a typical particle, as well as how many millions of people were exposed to that particle. On the right, if we add those distributions up, we can see that nearly the entire population, so 99% of the population, are exposed to particles that are on average smaller than PM1. So most of the population of China we found was exposed to particles that were smaller than PM2.5, smaller than PM1 in fact. And also we found that the mass concentrations to all the particles in this fine fraction were quite high overall. And if we examined the effects of those exposures over time on increased premature death, we found that from 2005 to 2017 over China, premature deaths associated with fine particulate matter increased by 31%. And this is despite PM2 concentrations that were falling, especially after 2013, when China introduced some more aggressive air quality controls. And the reason that it's still going up is that there's increasing population levels and increasing baseline health risks. So they cannot overcome the reductions in concentration. So we still have to work harder to reduce concentrations if we actually want to see a reduce in risk. And in particular, or alongside reducing concentrations, we could focus on reducing risk by addressing underlying risks in the two most important causes of death, which were stroke and ischemic heart disease, which explain most of the PM2.5 related premature deaths over the time period. These causes of death both peaked in the Henan province. You can see here, for example. Chronic obstructive pulmonary disease, or COPD, and lower respiratory infections, or LRI, did not contribute as much to the total, but they had a slightly different geographic pattern, peaking in Sichuan. And so given the different geographic patterns in terms of the health impacts, we were interested in understanding how equitably are these impacts distributed. So, if it was perfectly equal, every person would be equally likely to experience an increased risk in premature death. So to explore that, we examined the distribution of mortality impacts with income, which we represented it as GDP per capita. We used that to calculate something known as the Genie Index. The Genie Index is a measure of inequality, where a Genie Index of 0 would indicate that everyone gets their fair share of, in our case, deaths or dollars. And any distance away from a Genie Index of 0, which can go all the way up to 1, would indicate that normally it's the lower income folks that are more burdened or are not receiving as much of the wealth. So when we estimate this over China, over our study period, we found, first, we looked at the economic Gini. So this looks at how fairly China's significant economic growth over that period has been distributed across the population. And we found that positively it fluctuated, but generally trended toward more equality. So the rising tides are lifting all boats, is a term you might hear from economic growth theory. If we look at the distribution of health impacts across the country, we actually find they're highly equitably distributed. So it doesn't, your income level doesn't predict what your risk of dying from PM2.5 exposure is in this case. We were also interested, though, we understand that a lot of that economic growth is due to migration, where certain areas of the country are experiencing a greater economic boom than others, perhaps at the expense of others. And so we also calculated the equality between provinces in China. And economically speaking, we saw less of a change in increasing equality, but it still trended towards more fairness, which is a good thing. However, we did see a bigger disparity in terms of the health impacts between provinces. So this does imply that there are provinces that are experiencing an unfair share of death associated with air pollution compared to their neighbors, and that the lower GDP provinces are experiencing more of these health risks. Again, we saw that trending mostly towards more equality over time, which again is a good thing. If we look at the two causes of death that were most unequal, we can see the pink and yellow lines here in both cases. That was COPD and LRI, or chronic obstructive pulmonary disease and lower respiratory infection. Those were the two that had the different geographic pattern from the main causes of death. And what we found is that, yes, they are disproportionately affecting provinces with lower GDP per capita. We also saw that reducing concentrations alone wasn't necessarily enough to reduce the actual impacts. And so what we would recommend is that we could evaluate targeted policy to reduce the baseline risks in provinces with lower incomes for COPD and LRI, and this might help to combat some of this disparities in health outcomes that we saw. So this summarizes our study on China and the current conditions there, or at least recent conditions there. And this begs the question, okay, so if we have policy, or we suggest that policy might be able to help alleviate some of this inequality, what might that actually look like? What might we actually get from that? And so much of the work in my lab, and what I'll touch on briefly in the rest of the talk, are some of the solutions that we can adopt to reduce emissions, to protect of air pollutants, and also greenhouse gases to protect the climate and human health due to air pollution exposure. So moving from particulate matter in China to ozone in the United States, we'll look at health disparities there. Now, to be able to examine the benefits of policy solutions, we need to shift from data-driven methods to model-driven methods. And that's because models allow us to ask what-if questions. You know, we can picture different futures, often highly uncertain futures, in order to gain insights and try to push us, nudge the world onto a path that's more sustainable and more healthy. And to do this in our research group, we take what's called a model framework approach, which means that we attempt to represent the chain from the implementation of a policy to its effects on the atmosphere, on human health and the economy. And we call it a framework approach because we have to use different modeling techniques to represent different components of this system, depending on the scale we're interested in or the source we're interested in. And here we're applying that integrated modeling approach to look at the effects of ozone pollution on human health and the benefits of ozone reductions. So here we're looking at the United States, and we have represented ozone concentrations in the year 2005, as well as reductions that were planned back for 2014. And we're representing the incidence rate of premature death associated with ozone. So that's the number of premature deaths per 100,000 people per year, along with household income groups. And what we can see is a classic pattern of environmental inequality, where the lowest income households are experiencing the highest risk of mortality associated with ozone exposure. That's true in 2005. And after the reductions, the planned reductions, we can see that mortality risk drops for everyone. And maybe it's not quite so steep. Maybe there's some alleviation of exposure inequality here. However, we can really see the benefits of the policy in terms of addressing some of these environmental disparities when we look at the economic welfare change. So we associate the change in ozone exposure, not just with change in mortality, but changes in illness as well. You know, having to use asthma inhalers, having to go to the doctor, missing school days, and things like this. We can apply the economic value of this and understand how much better off folks are under the policy compared to under no policy. And so when we do this, we can measure the economic welfare change under the policy. The economic term is equivalent variation. And again, we can review this by household income group. And what we see is that the welfare gain for the lowest income groups is, around, 0.22%. Compared to the highest income groups, it's closer to 0.1%, which means that the policy is, relatively speaking, twice as valuable for the lowest income households as for the highest income households. I also mentioned that it looked like maybe the policy reduced disparity in exposure in terms of who's living in the highest ozone areas a little bit. And it did a little bit. And we can see that in the blue shaded area where we examined the contribution of that change in more equal exposure. But it doesn't really explain a lot of the steep grade in terms of the relative benefit for the lowest income households. What really is explaining that is the underlying economic disparity. When you don't have a lot to begin with, giving you a little bit more is just worth that much more, relatively speaking. And that's why implementing the policy is relatively more important for folks in low-income groups, and why delaying the policy, which is what actually happened in the United States. It was challenged in the courts and delayed. And what that does is hurt everyone. There's a welfare loss represented by the red shading, especially more so the lower income groups, of course. All right, and in my last 5 minutes, I'm going to discuss a little more about some of policy solutions, because in particular tying it to climate change. Because even though this talk is, or sorry, this conference is about air quality, the leading environmental health issue today, climate change is undoubtedly going to be the greatest health threat that we face over this century. And it's inextricably linked to the problem of air pollution. So a lot of the research that we focus on now is trying to consider, how do we address these problems which are linked together in a coordinated way, in a sustainable way. So climate change, we know, is going to have a variety of effects on our environment: rising temperatures, changes in weather and circulation, higher change in atmospheric composition. And that's going to affect a whole bunch of other things that are exposures that affect our health, from air pollution to water quality to pathogens, allergens, etc. And of course, this includes air pollution and the associated diseases that we've already talked about. What this means is that if we address climate change, then solutions to the climate problem can have significant local and near-term co-benefits for our human health. So for example, green diets are healthier diets, and active transportation is healthier for us. And if we reduce dirty sources of carbon emissions, we're also cleaning up the air, and this offers health benefits. So you can see that here, for example, one of the first keynote talks talked a lot about emissions from diesel for transportation, for example. And so if we were to switch from diesel-powered vehicles to electric vehicles or hydrogen-powered vehicles, we would not only be eliminating those emissions of greenhouse gases like CO2, we'd also be eliminating all the other air pollutants that come out of that tailpipe with them. That would then improve air quality, yield health benefits, and associated economic benefits. And those are called co-benefits. So if we don't address climate change, if we do nothing about emissions, then air quality is going to get worse. In fact, we've found from our studies that are focused on the United States and Canada that we could lose, with all the hard work we've done over decades in improving air quality, we could lose nearly half those gains in terms of the health risks if we don't meet our climate targets. Conversely, though, if we do meet our commitments under the Paris Climate Agreement, then we are protecting ourselves from nearly all of that risk increase. And there are very cost-effective ways to do this that can lead to significant local benefits for us. Even though climate change is a big global problem, the benefits for air quality mean that we can reap benefits in our backyard, especially if we design a cost-effective policy. So here we've examined 3 different climate policies that all reduce the same amount of carbon emissions. And I've only plotted here on the y-axis just the benefits that are associated with improving air quality. So it's a climate policy, but I'm only looking at the benefits that happen to air pollution. So this is just the co-benefit from improving air quality on the y-axis. And here's the entire climate policy cost in a given year on the x-axis. So this is very not fair comparison. The whole climate policy cost just compared to the air quality co-benefit. And we can see for 3 different types of policies that the air quality co-benefits are all pretty high for all 3 types. So we're cleaning up the air if we're combating climate change. But the more different sources of that we bring into the policy, the more cost effective we make it, all the way down here to the carbon tax, we can see that the cost gets so low that the air quality co-benefits totally exceed those costs by up to 10 times. So anywhere here in green, the air quality co-benefits alone are higher than the cost of the whole policy, which is hopefully motivating in terms of addressing both of these issues. So I know I've covered many topics, but if I can leave you with one overall conclusion, our work shows that air pollution is a major issue for human health, that it has unequal impacts. However, if we design policy to reduce emissions from many sources flexibly, then we can protect human health, promote equality, and meet climate goals in a cost-effective way. So with that, I'd like to acknowledge the many people who have worked on this and have helped fund the work. But I thought I would end with showing my wonderful lab. This is what a PhD student looks like. Hopefully one day it will be you if you're not yet. And I want to say thanks very much, and I'm happy to answer any questions.
Thank you, Dr. Rebecca, for your interesting presentation and comprehensive topic. I'm sure that the audience have enjoyed it. So from the audience, are there any questions you would like to ask Dr. Rebecca?
I've overwhelmed them.
Can I ask a question, Ali?
Okay, yeah. Yes, Iman.
So just to double check on my understanding, does your experience use satellite data, or do you use pre-installed devices? And how easy is it to access this data?
So I think I heard, do we use satellites or pre-installed devices? Do you mean ground level monitors?
Yeah.
Right, so we use ground level monitors. So we use a combination of data sources. I didn't get into the full methodology. We use optical properties from satellite data, which is provided. The aerosol optical depth products are provided online from the instruments, and we combine this with some ground level data information for verification primarily. So we use the ground level monitor data from China, which my student, Dr. Ming Liu, also acquired mostly from the Chinese government, but going back farther, she had to piece that together from different sources. And we also used meteorological data, for example, which we got from MERA weather reanalysis. So there was a variety of different data sources that we needed to combine into one model that would help predict PM 2.5.
Thank you. Another question, please. Does the PM 2.5 affect the ozone layer?
Okay, interesting question. So, the ground level PM 2.5 at the surface, which is what we studied here, probably doesn't have too much of an influence on the ozone layer. When you say the ozone layer, normally that refers to stratospheric ozone, which causes issues in terms of increased UV radiation at the surface. Is that what you mean by the ozone layer, the one in the stratosphere?
Yes, that one.
Okay, yes. So I wouldn't say that the surface PM has a big influence on stratospheric ozone, but I will say, they're pretty separate. However, the stratospheric ozone depletion chemistry is heterogeneous chemistry. So it does take place on, at the poles and things like polar stratospheric clouds. And so those are little aerosols in the air. In a sense, particulate matter aerosols do play an important role in the chemistry that really leads to stratospheric ozone depletion. But I don't know. Okay, yeah. I guess I'll add, I haven't seen research talking about surface PM affecting the stratospheric ozone, but I have seen studies interested in global solar radiation management, so geoengineering, to fight climate change, have looked at seeding the stratosphere with aerosols, and that does affect PM 2.5 at the surface.
Okay, can I ask a question, Ali?
Yes, sure, Mr. Umar.
Yeah, thank you, Dr. Rabika, for this interesting presentation, and thank you, Ali, and the colleagues for organizing this interesting, wonderful meeting. Dr. Rabika, my question is that you are using satellite data, remote data for predicting or calculating your, feeding your model. In how much you feel that this is in coordinates with, for example, if you are going to measure particulate matter, there is a lot of uncertainty in measuring this by satellite data. So how you just differentiate between long range and local sources, especially when you talk about where areas there is local fugitive dust or dust storms. Thank you again for your nice presentation.
Thank you. Thank you for the interesting question. Yes, we use satellite data in the exposure analysis study, the first one we talked about. And you're right, we don't use those data to differentiate the source of the PM. We're only using it to look at the mass of PM and get some understanding about the size distribution. So no, we can't tell just by looking at the data where the PM came from. And yes, that's especially difficult looking through a column of atmosphere. In my own work personally, if I'm interested in connecting sources to receptors and receptor impacts, I use models for that. So we will chemical transport models usually. So we have full emissions inventories, detailed emissions at the surface, and we can predict the chemical transformation and the dispersion of those emissions and how they affect concentrations in a given area. So that's how we would look at things like local sources versus long range transport. Now, of course, you saw in the first keynote talk, there are other ways of differentiating source impacts as well, things like chemical mass balance and positive matrix factorization, and you can use back trajectory analysis and things like this. But no, we weren't trying with the satellite data to differentiate local versus non-local sources. What we are seeing is the combination of all of that chemistry and transport from local and non-local sources.
So thank you, Dr. Sari, for answering our participants' questions. I would like to thank you again for accepting our invitation to this conference and for your lovely presentation. We hope to meet you in our coming events as well.
It'd be my pleasure. And please, if anyone has any other questions, don't hesitate to reach out by email.
Thank you, Dr. Rebecca. So I would like to apologize for being behind the schedule, everyone. Now I will be introducing to you my colleague, Mr. Hussein Boumehdi, who will host the next 2 hours, the second half of the conference. So Hussein, can you hand on the conference or here?
Yes, hey Ali, how are you?
Hi Hussein, I hope you're doing well.
I'm doing great, thanks Ali. Hello everyone, welcome again. It's Hussein. I'm the conference and mentoring team lead at ReachSci. I'm also a second-year master's degree in translation and cross-cultural communication student and the director of cinematography in an environmental award-winning documentary series called The Guardians of the Environment. I hope you're enjoying our talks, and now we'll be moving to the next talk by one of ReachSci partners, Lorena Gordello. Lorena Gordello is a multidisciplinary engineer passionate about the power of citizen science and community-driven spaces to find solutions to today's world problems. After completing a general engineering degree at the Technical University of Madrid, she is now doing her PhD in biosensors at the University of Cambridge as part of a doctoral training program in sensor technologies for a healthy and sustainable future. Lorena is also the co-founder of the Open Seneca initiative, which deploys mobile air quality sensor networks driven by citizen science. The initiative aims to raise awareness among citizens about personal exposure to particulate pollution to drive behavioral change and build high spatial and temporal resolution pollution maps that inform policy and urban development. Ms. Gordello, nice to have you, and please go ahead.
Hi everyone, thank you for the introduction. Okay, so today I'm here to tell you a little bit about the work we do at Open Seneca. You've heard a little bit of the current student projects where they use the sensors for to measure particulate matter in the kitchen, but we actually work much more broadly, and I want to tell you a little bit about it. So I think we've talked today already a fair bit about the problem of air pollution, but I think we've talked about the reduced life expectancy and the fact that over 90% of the population is actually living in places that exceed the World Health Organization guidelines. And mostly this problem comes from that the equipment to monitor, the reference level equipment to monitor pollution is actually very costly. And in a lot of the developing countries, is not affordable. And that means that there's not enough data to really understand and tackle the air pollution problem heads on. And also there is a lack of general awareness about the health problems linked to poor air quality. So we've discussed some of those today, and they're also more and more in the news. So what we do with Open Seneca is that we use these local sensors that are mobile. So they are battery powered, so they can be carried around the city. And we use citizen science, which means involving citizens into collecting air quality data and understanding the air quality data. And we map the cities with this street by street. So the way we involve citizens is that we involve them, we want to involve them in all the phases of the project. So basically from understanding the technology and being able to assemble their own air quality sensors and workshops, to then collecting data, and then importantly interpreting, bringing meaning to the data. So once you've monitored a city street by street, it's actually important to understand why specific areas are more polluted than others and bring the local knowledge there. And finally, taking action. So we always encourage our participants to brainstorm solutions as we've done today in this conference. A lot of the students were talking about solutions. We just heard about some of the policy aspects of it. So we think that the more people thinking about this problem, the more solutions we'll be able to find. So we work with this air quality sensor that basically has a particulate matter sensor from these brands in Syrian. This is a local sensor that basically works by light scattering, so it shines a laser onto a flow of particles that's driven by a fan, and then from how the light is scattering, you can estimate what's the particle count and the size of the particles. So we also have this sensor has, it's battery powered, and it communicates via an app with a Bluetooth And it also has like temperature and humidity sensors and GPS. We talked before, I think Professor Harrison is not on the call anymore, but we talked before about the quality of the data collected with these sensors. So of course they are low cost and their measurement technique is less accurate than the one of the bigger reference stations. But we do carry what's called colocalization studies, which means that we place all the sensors on top of one of these reference stations and we measure for a period of time. This time I was on, this is an example in Lisbon for 2 weeks. And you can see, so our sensor readings are the green and the reference station is in red. So you can see that although we underreport the values of PM2.5 compared to the reference, it actually does follow the same trend and we can apply a calibration factor to this. One of the important things is that all of the sensors come calibrated from factory and actually are very, very consistent with each other. So you can see in the graphs here, they are all within 1 microgram per cubic meter readings. So I know you mentioned that some of the students, there might have been one sensor that was faulty, but generally they're actually really consistent. And once we apply this calibration factor, actually, we can actually really provide indicative values for the city that are consistent with the reference data. So I wanted to tell you a little bit about some of the projects we're doing. We're doing more at the moment, but we've been working recently in Lisbon and Stockholm as part of a Women for Climate Tech Challenge, together with C40s and financed by Velux. And we've had deployed 50 sensors in each city. And the way we work is that we work with local champions, which means that we partner with local organizations that can then organize the workshops and they engage their own citizens. And in this case, we've partnered with like Fab Lab of Lisboa, which is like a fabrication space, a community space used to organize workshops and activities. And then a cycling organization and a university group for sustainability at KTH in Stockholm. And then we organized a series of workshops where people could assemble sensors either in person or at home because of the COVID restrictions. And then we are currently collecting data and organizing data hackathons to let people bring meaning to the data. So I just wanted to share a little bit the results so far and speak more focusing. We talked today about more technical aspects of particulate matter monitoring. And this time I would like to speak more about the citizen science side. So we had an open call for volunteers in both cities, and we got a very great response rate. So over 150 people were interested in participating. And some of the motivations were, well, that they cycle all day, so they're happy to contribute to this project. But mainly it was about really being interested and curious about what's the air they're breathing. So they're interested in the environment, sustainable traffic issues, but what they really want to know is like, how is the air we're breathing? We ran a small survey to understand the background knowledge. And interestingly, more than half of the responses showed that even though they might have heard of it, they actually didn't really know what citizen science or PM2.5 is. So there's confirmed a little bit the problem of lack of awareness. And also most people thought that air pollution hasn't affected them directly, but some other people reported that they know friends and relatives that it has affected, or they've had some either physical or respiratory problems in the past due to air pollution. And I just wanted to share some pictures about the activities. So we run these workshops to teach people about air pollution and health impact, and then give them the opportunity to build their own sensor. So these are some examples in the 2 cities where we were able to organize in-person workshops, or people assemble the sensor at home with following some video instructions. And people say that actually building the sensor makes them feel much more engaged with the topic of air quality and air quality monitoring. So we think it's important to engage everyone in all steps. And then we distributed the sensors. So these are some pictures from the distribution event in Lisbon. And what we do is that we encourage people to carry the sensor and use it in their daily activities. So it could be while they commute in the city, or it could be while cooking at home and try to figure out, should I turn the extract on or not? And then people can actually also write comments and bring, as I said, meaning. So if you notice, like in this case, this here in Cambridge, there was like this peak of pollution that goes all the way to 60 micrograms per cubic meter. around a river area. If you don't know the place or the city, you would say like, why is this area polluted? It's like a beautiful park, is a river. And actually only if you cross that area and you figure out, you might know what's happening and identify the source of pollution. And then once you know the source, then you can take action. And in this case, the source was like that there is reports burning coal. So we encourage people to use this function. And once we've had enough people using the sensors, then we can generate maps of the city. So this is one for Stockholm. And actually we could calculate what's the baseline of the city and then pinpoint what areas are consistently above the baseline and then become hotspots of particulate matter, where then we should focus our resources to try to understand what are the sources there and then take action. And another result of this data collection is that as well, we get the users themselves to share in social media their own results and actually start a discussion about air quality. As much as today we started a discussion about cooking methods and like what's the best way of cooking. So just to finish, we've been scaling up this initiative. So we started here in a small pilot in Cambridge, but now we've moved to many other places. So we're basically in Latin America, Africa, Asia, and working with a number of partners that we would like to thank, including the UN and C40 cities. So with this, I would like to thank you all. And if you have any questions, I'm happy to answer.
Thank you so much, Ms. Gordello, for your interesting presentation as well as the initiative. We're sure the presentation was engaging for our audiences. Please ask your questions to Ms. Gordello.
Yes, Bawadi, can I go for question?
Yes, go ahead, please.
Dr. Lorena, thank you for this very interesting and promising initiative. I congratulate you for this study. My group also, we are working in similar studies, doing sensors just for indoor air quality during COVID-19. So you know that we now focusing on the indoor air quality, especially for schools, for hospitals, for shopping malls. My question, what kind of pollutants you are focusing on besides the particulate matter? And do you think that your initiative can be extended also for stationary places like schools, especially kindergartens during the COVID-19? And thank you again for your initiative.
Thank you for your question. So at the moment, we're only focusing on particulate matter. We're not measuring any other gases or pollutants, mainly because it's the one that has the biggest effect on health. And although our sensor is designed to be mobile, so that's why it's battery powered and it's meant to be carried in daily commutes, it can be used indoors and it could be placed on a fixed location. And we're actually having a few projects with schools to get the kids as well. So have some placed in the schools, but also get the kids to interact with the sensors and use them around the school environment. So that's definitely something we were keen on exploring. And the sensor can be just plugged to the main power. So in that sense, they can work stationary without having to rely on the battery power.
Thanks, Omar, for the question, and thanks, Ms. Gordello, for your answer. I have also a question from Dr. Rebecca Seri. The question is, what is the strangest comment you have had from a user?
Yeah, I read it and I was thinking about it. Most of them are quite common. I like either street food or like construction sites. What's the strangest one? I think they've been all pretty common. I think I don't have a crazy answer for this question.
Yeah, it's okay. Definitely takes a lot of thinking to get a decent answer in this short amount of time. It's okay. Well, once again, thank you so much, Ms. Gordello, for being with us first and for your inspirational presentation. We hope to meet you soon, inshallah, in our upcoming events. Thank you.
Thanks.
We'll immediately move now to our first presentation by Abdullah Iberi. Mr. Abdullah Iberi is a PhD student affiliated with the Materials and Environment Laboratory, abbreviated LMA. He works on air quality monitoring in urban areas in order to intervene in critical cases of air pollution by particulate matter. And he will be presenting today on experimental and numeric study for the prediction of the concentration of particulate matters PM 2.5 by using SVM algorithm. Mr. Abdullah, welcome, and please go ahead. Mr. Abdullah, please unmute your mic. I can't hear you. We can still not hear you, Mr. Abdullah. Please unmute the mic. Yeah, we can now. Please go ahead.
Hi, Mr. Chairman. Hi for all participants. Today I present to you a research work concerning experimental and numerical study for the prediction of the concentration of particulate matter PM 2.5 by using SVM algorithm. I started by abstract it from work. This work aimed to model the daily evolution for particulate matter concentration PM 2.5 based on meteorological factor. By using the Dragonfly SVM algorithm, early data on atmospheric concentration of PM 2.5 and the meteorological factor were recorded simultaneously at an air quality monitoring station located at an urban site in Algiers using the FIDAS 200 fine dust measuring device. In this study, the Dragonfly meta-heuristic algorithm was used to select the optimal hyperparameter of the supervector machine model. For this, a MATLAB program based on the Dragonfly optimization algorithm coupled with the SVM regression algorithm was written in order to correlate for the PM 2.5 concentration. The obtaining results show that the established model has a good predictive performance with a correlation coefficient R equal 0.99 and the mean absolute error equal 0.62. Secondly, methodology, measurement area and period. The measurement seat of the air quality analysis station NISMA is situated at the Hospital University Center, Mustafa Pasha, downtown Algiers. Algiers, the capital, is the most populated city in Algeria. Algiers is characterized by a Mediterranean climate with a humid and hot summer and dry cold winter. And the average annual temperature is around 22 degrees C. The measurement seat is located approximately 600 meters from the sea. It's open to the sea, therefore undergoes good natural ventilation. The early data of conventional fraction PM 2.5 and weather factor, temperature and relative humidity were recorded simultaneously using FIDAS 200. Additionally, the wind speed and the cumulative precipitation data were collected from the National Meteorological Office of Dar el Bayda, Algiers. The duration of sampling was carried out over a period of 4 months from February 1 to May 20, 2019. To modeling of experimental measurement. The supervector machine SVM is one of the machine learning methods. The objective of SVM is to find the nonlinear regression function to produce the output Y based on training data ND. An SVM model take the the form equation 1, where represents the nonlinear function, omega represents the vector of the weight, and B represents the bias of the regression function. To obtain a successful SVMR model with a good predictive capacity, there are 3 parameters that need to be carefully chosen. This parameter, called the hyperparameter of the SVM model, included the penalty parameter C, the coefficient of non-sensitivity epsilon, and the parameter of the bond width of the Gaussian nucleus RBF sigma. Therefore, the meta-heuristic method of the Dragonfly was deployed to optimize the hyperparameter of the SVM. In this work, the DA-SVMR algorithm was produced to obtain a PM2.5 concentration prediction model, which is more powerful and robust for solving a nonlinear problem. Third, results and discussion. After selecting temperature, wind speed, the relative humidity, precipitation, and factor of choice as appropriate input parameter, and the concentration of PM2.5 as output, a kernel function is required for the implicit mapping of learning model in the functionality spaces. The experimental data are divided into a learning set and a test set. Each data set must be well distributed in the model space. Consequently, 80% of the entire data is intended for the training set, and 20% of the entire data is also intended from the test data set. To evaluate the predictive capacity of the optimized SVMR model, MATLAB function postreg is used for plotting the data set of learning and validation predicted various experimentals. The performance result of the model of a neuronal network established for the learning and test phases for the concentration of PM2.5 is presented in figure 2. Clearly show that all the points are located on the first bisector with a regression coefficient approaching the ideal. I'm excused for this.
It's okay, Mr. Abdullah.
To analyze this, to analyze SVM RNO performance more precisely and correctly, the error formula and the coefficient of determination and correlation R square and R are calculated for the concentration of calculated PM2.5. The calculation results are shown in table 1. The RNA show that on the one hand, the calculation prediction of the rate of the active carbon return, and on the other hand, the robustness of the neural network. Conclusion, the work was carried out over the period from February to May 2019 to measure the concentration of PM2.5, temperature and relative humidity in an urban site located in downtown Algiers using the FIDAS 200. Measuring device wind speed and precipitation were collected from the organization National Meteorological. The numerical results were the object of the modeling by DSVMR of the 2.5 concentration measured as a function of the meteorological condition. The advantage of this mathematical model is the ability to solve the nonlinear problem for the complex phenomena. The Dragonfly algorithm was well optimized. The hyperparameter C, sigma, and epsilon of the SVM model and is demonstrated by the good alignment of the predicted data set as a function of all the experimental data on the first bisector regression. The coefficient of determination R-square and RMSU have shown that the results are promising. And thank you.
Thank you so much, Mr. Abdullah, for your presentation, and thanks for accepting the invitation and being with us. We hope to see you in the upcoming events. And we will move directly, because we are behind on time, to our third keynote speaker, and the presentation by Dr. Brian Caulfield. Dr. Brian Caulfield is an associate professor and head of discipline in the Department of Civil, Structural, and Environmental Engineering at Trinity College Dublin. His research focuses on the optimization of transportation networks with the goal of reducing emissions and meeting our climate change targets. Dr. Caulfield has published 80 peer-reviewed journal papers on the topic of transportation and is an editor of transport policy and the senior editor of Renewable and Sustainable Energy Reviews. His topic for today's presentation is using floating bike data to determine cyclist exposure to poor air quality. Dr. Caulfield, glad to have you with us. The floor is yours.
Thank you very much. I am going to try and share my screen. If I can just, everybody can see my screen?
Yes, Dr. Caulfield, it's good.
Okay, thank you very much for the introduction. And it's a great pleasure to be with you here virtually this afternoon. So I'm based in Trinity College in Dublin, and I'm the current head of Department of Civil, Structural and Environmental Engineering. The research I'm going to talk to you about today is around bike data that we have in the city that we use to measure exposure to poor air quality. In terms of context, my background isn't in air pollution or air quality. It's much more in transportation. But some of the results around the OSM model, one of my colleagues would be better to speak to you today on. But I'll do my best to answer any questions that come at the end. Okay, it's working. Sorry, I just tried to get to my next slide. Okay. So just in terms of the presentation, I'll go through an overview of the problem setting that we had within the project here in Dublin, the data and the methods that we used, the economic valuation of air quality. So working in transportation, this is one of the things that I work on quite a bit, is how you measure impacts of transportation. And we did this with the economic valuation of air quality in this paper, and then talk to you about some of the results and then some of the conclusions. So just to start off with an acknowledgement, this paper was done by Mr. Ian Smith, who was with us in Trinity doing his master's degree. So all of this research came from his master's thesis. And I was also helped by Dr. Shreya Day, who completed a PhD under my supervision, looking at emissions from transport. This paper is available online using it's available, through Science Direct, and it's open access, so you should be able to get access to the paper if you want to. And once I'm out of shared screen, I will I'll put the link in the chat. So in terms of the problem setting, the World Health Organization claims about 9 out of 10 people breathe in air that contains high levels of pollutants. And while air pollution itself is responsible then for about 7 million premature deaths every year. So this was one of the key obvious drivers of the work that we conducted. Pollution from fine airborne particles is responsible for about 725 deaths in Dublin annually. Dublin has come a long way in terms of its air quality, but still it's not perfect. The EPA, our Environmental Protection Agency here in Dublin, in its annual air quality report found that there was about 1,300 premature deaths, and this was up from the number in 2016. So that value was from 2019, and this was up from the number of premature deaths in 2016. So the problem around air quality isn't getting any better in the city. These issues, coupled with the increase in walking and cycling within the city, has both have large concerns for the city authorities and also for the research that we conducted. So to give you some context around the city in which we operate, so this is Dublin City Centre. I'm sorry, my dogs at the moment are barking outside of my office. This is Dublin City Centre, and each of these numbers basically is a bridge that goes into the canal cordon. So we've got two canals either side of the city, and inside of that is where the majority of the city centre is and where the majority of people live in the city. Every year in November, we count the numbers of people that travel into the city cordon to get an idea of the number of people that travel by bus or by car, walk, or cycle. And this has been done for over a decade, this type of information. So what we wanted to do in this study was to model parts of the city centre and to find out where the pollutants were at their highest and what we could do about that, measure the impacts of that. So this slide here shows you the percentage mode share. So from 2006 to 2019, all of the data here was up until 2019. This research was done during COVID, and that causes some kind of, I suppose, caveats that I'll mention later on. But in 2006, you could see that the car accounted for about 38% of all people movements into the city centre. And then in 2019, you could see this had fallen by 11%. Similarly, you'll see increases here in walk and in cycle over that time period. And equally, an increase in public transport use as well. So what this then basically, it gives us the concern then that passengers that are walking or cycling, or indeed using public transport to get into the city centre, are exposed to unsafe and high levels of air pollutants in different parts of the city. Oh, okay. This is slide. No, sorry. So to work out the first thing we needed to do is we knew we wanted to work at cyclists' exposure to pollutants. So the first thing we needed to do was to find a good data source on cyclists in the city. Unlike, say, cars and public transport, that there's a large amount of data associated with them for how they move around a city, there's very little information on how bikes move around a city. So this floating bike data came from a company in Dublin called Bleeper Bike. And Bleeper Bike basically provide a bike share scheme where people can hire a bike to travel around the city. And when they do so, they're tracked using their mobile phones. So we're able to get a very good approximation of how many cyclists are cycling around different parts of the city. And this is just a screenshot of the type of data that we got back from the bike company. So we got the serial number of the person. This was not something we were very interested in. However, the timestamps were something that we were very interested in. And then obviously also the GPS coordinates. So we could see people as they traversed the city where they were traveling to and from. Then this next slide shows you a heat map that we conducted or that we produced of the data that we collected. So you could see where the numbers of people that were cycling. In the city, we have a number of fixed point cyclist counters, but they tend to be at very kind of obscure parts of the city. And to get a good measure of the numbers of people cycling, we decided this floating bike data was probably going to be the best. So you can see here along the canals that there was, so you'll see this natural canal that goes around the city here. We could see that there was a large amount of people cycling along those canals back in 2019. This is not surprising because there's a very high quality, cycling infrastructure on either of the canals, which encourage people obviously to cycle. And that's where we got it. That's where we got the majority of our data from on where these people movements are. And then using this data, then we decided to examine where within the city were people moving the most, and then to pick out 2 or 3 roads that we would do some more detailed emissions modeling on. So these were the roads that we looked at initially. You can see one here. So those of you that aren't familiar with Dublin, here's Trinity College here. This was Dame Street. This was one stretch of road. Then this other stretch of road that went out as far as the canals was the second piece of infrastructure that we road infrastructure that we looked at. We looked at another one here towards Rathmines. And there was also a small section of road here through Balls Bridge that we also took account of. The one thing to note about this piece of infrastructure, or this road or this line here, is that it links a very residential part of the city into the main kind of central business district. So in and around here, this area here of Dublin has the majority of people that work in the city, be they in the university or in government, or around here is where a lot of the large international tech companies like Google, Facebook, TikTok, etc., they all have their European headquarters in that part of the city. So these were the roads that we looked at. So we needed to get this data on how many people were cycling there, but then we also needed to get data on the numbers of cars that were traveling. So this screenshot is from a system that we have in Dublin called SCATS. So basically what SCATS does is it counts cars as they travel throughout the city. And back in we got the data from 2019 of the numbers of vehicles that were traveling throughout the city at each of the different points that we were interested in. We also, we have to make assumptions around the fuel types that they were using, whether they were using diesel or whether they were using petrol, and then also the types of vehicles that were traveling through the network. But we got very good data from Dublin City Council on the numbers of people, the numbers of vehicles that were traveling through the city. One of the things, I probably should have said this earlier on, was that in Ireland, we tend to have a very high percentage of our vehicle fleet is diesel. This is for a number of different reasons, but then obviously, as many of you will know on the call, that this then has very bad impacts in terms of air quality with regards to carcinogenics, etc. So that was that was a motivation that we had in doing the research. But this then basically, so we've got the data on the bikes and then also the cars by collecting this data from Dublin City Council. This is just an example of the type of data that we got from the City Council. So you've got the volume in vehicles here in terms of thousands, and then the hours of the day across the bottom on the x-axis, and then the different roads that we were looking at. And obviously, as you would expect, anybody that's looking at traffic data will know this. There's obviously a morning peak and an evening peak, and we were able to work out what the volume of traffic was that traveled through the network. So one of the methods that we used was a piece of software called Copert Street Level Model. Basically, what this does is it breaks down emissions into different road links, so you can have an idea of the amount of emissions that are likely to be put out at different parts of the city. In Ireland, Copert is the model that the Environmental Protection Agency recommend that we use when we're doing any research for the government, because it's the one that the standard that they use. I'm not sure where everybody is on the call, but I think in the UK they use something different, but it's based upon some of the principles of Copert. So what we had to get was the average road link length. We had to get the hourly volumes of traffic, and we also had to get the road link average speed. Then the different types of vehicles: passenger cars, light good vehicles, heavy good vehicles, and motorcycles. And then we needed to get these by the fuel type, the vehicle size, and the Euro class. The Euro class then denotes the amount of emissions that come from the vehicle, or how efficient it is. And then at the end, Copert will provide us with all of this information related to the different emissions that are likely to happen on that street. We've used it before in the city. Again, you'll see this in this kind of 3D model here. You will see this was work done by Shreya Day. You can see the canals here, and you can see the peaks at which emissions happen throughout the city. And this is an earlier piece of research that we did. And you can see where there's spikes here. This part of the city has very high levels of pollutants because of a large number of buses that use this corridor here. So this is how we estimated the link lengths. We went into Google. So all of this was done during COVID. So the student that was doing the research wasn't actually based in Dublin, and he was based in a different part of Ireland. So a lot of this had to be done remotely. A lot of the kind of validation and calibration that we would normally want to do with these types of projects wasn't possible, mainly due to the inability of the student to get into access out onto site. So here you can see the link lengths that we looked at. So this is Dame Street, and you can see how we estimated these link lengths. And then in this diagram here, you'll see this is Dame Street again. At the very bottom of the street, you'll see Trinity College. And then you can obviously see that one of the things that we had to get as well was the heights of buildings, because along with Copert, we also use an OSM model to work out the concentrations of emissions, and that was needed for the burden of disease approach that we took to working out the health outcomes of the research that we conducted. So the students used Google Earth to estimate the heights of the buildings to look at the canyon effects that were happening throughout the city. And again here, and this maybe, I apologize for not being on throughout the rest of the day, and having looked at the program, there was lots of really, really interesting pieces of work, but I was stuck teaching. But here you can see this is why we looked at it, for this kind of canyon effect, that we needed to work out what the concentrations were at different points throughout the canyons that we were looking at in the research. The method then that we used was from the World Health Organization, and this is the burden of disease approach. So here with this, you have your air quality changes, the health effect estimate, the underlying mortality rates, and then the exposure to pollution. All of these are the factors that are put into this burden of disease approach. And what it can do is it can estimate the number of fatalities or premature deaths that happen due to poor air quality, but then also it can also estimate the years of life lost due to poor air quality. And these were two of the main factors that we looked at the end of the research. We looked at a number of different scenarios. We had ideally looked at doing other things, but again, COVID kind of got in our way. But the base scenario was the current fleet in Ireland. We looked at the current fleet that was traveling through Dublin city centre. The first scenario was that a minimum of Euro 6 diesel engines and Euro 3 petrol engines would be the minimum that would be in the city. So this was an improvement. Scenario 2 was the complete removal of diesel engines for passenger cars and a minimum of Euro 3 for petrol cars. And then the final one was a 10% reduction in all traffic to see what would happen in terms of the burden of disease and also the concentrations of emissions that we were finding. I said initially that we estimated the economic variables in terms of the costs of emissions. We use the pre-standard ones in Copert, but these are the ones that are recommended by the Irish government. Anybody that's on the call that's working in transport in the UK, you have something similar called WebTag, but this is our equivalent in terms of how we estimate emissions from different modes of transport. So here you can see this is for NOx emissions per kilometer driven by each of these different modes of transport, what the emissions concentrations are. And this is very, this is quite useful in a very quick and easy way of working out what emissions are using these different factors. But then to work out specifically the economic variables, we use these values here. So you've got CO2, NOx, VOCs, and particulate matter. And these are the values per ton of emission that the Irish government use. So for CO2, it's €20. This has increased since when you add on different factors. But I suppose the one of interest here is this one here of PM 2.5. You can see it's split between urban, suburban, and rural. And the reasoning behind that is because obviously in urban areas there's more people exposed to PM 2.5, so the health outcomes are worse. There is an argument at the moment that NOx would also be split out in this way in our values that we use, and these are the ones that would be specifically put into something like a cost-benefit analysis. So here are some of the results. So the lion's share of the work that was done on this in this research was really around the estimation and getting the data and getting all of the values in place. And then the results from Copert and the burden of disease model and also the OSM model, they were pretty quick to estimate and calibrate. So here you can see these are different sections of the streets that we looked at in the city, and this is just for Dame Street. So the base scenario in terms of the daily NOx in tons was 2.2, with scenario 1, which was scenario 1 was the improvement to Euro 6 for diesel and Euro 3 for petrol. Scenario 2 was the removal of all diesel vehicles, and you'll see that has the biggest benefits throughout all of the results. And then the final one was what would happen with a 10% cut in traffic. So the values here then in terms of cost implications are the values that we had, and I showed you in the last slide, and they were basically multiplied to work out what the benefits would be if each of these policies were any of these policies even were put in place. And this is one of the key things in our city at the moment, is this air quality issue. And while we're obviously, like every other country in the world, trying to reduce our carbon emissions, it's the air quality issue isn't something that you can disassociate from reducing your carbon emissions, especially when in past government policy was to put diesel fuels into our car mix. This then shows the concentrations of NOx on either side of the road. This was mainly Shreya's work because she's worked with one of these OSPM models before, and to work out what the concentrations were at a street level. And then using this data, it was then inputted into the burden of disease approach to work out what the outcomes were likely to be. All of this is cataloged obviously in the paper, and as I said, once I stop sharing my screen, I'll send the link to the paper in the chat. So these are the results from the burden of disease approach. So or is the relative risk on each of the different sections that we looked at, and the AF is the attributable, the amount of emissions that is attributable to the people that are cycling on the roads. E is the expected number of premature deaths, and then YLL is the years of life lost. And then all of these also then have an economic, excuse me, an economic value associated with them, to work out when you're trying to come up with policies for government to reduce emissions or to change the fuel type, or in some cases even bringing clean air zones. This is the type of data that we would put forward. So as I said, the results are quite short in that for each of the different scenarios, but the scenario that we found to have the greatest impact was the banning of diesel vehicles within Dublin city centre. So the results from the burden of disease approach, it showed that there was about 37 premature deaths from cyclists due to the pollution levels within the city centre. The cohort results also showed that changing the Irish fleet from outdated Euroclass and diesel engines together could result in a drastic change in emissions levels. The results from scenario 3, where we were taking out 10% of the traffic, did show that there was a linear relationship with the amount of emissions that would be saved. So as governments, one of the key things that kind of came out of the research at the end was that as governments continue to push commuters towards sustainable modes of transport, we need to consider what the impacts are likely to be in terms of air quality if we're still allowing diesel and higher pollutant vehicles use our city centres, specifically in very dense parts of our city where you do have these street canyons and the concentrations of these emissions can be quite high. So along with a shift in mode choice, the change must also be made to implement in terms of the vehicles as well, and the standards of these vehicles and how we change these. So while it's difficult to introduce the private vehicles, lots of parts of Europe have looked at these low emission zones, and I know in London that they have one, and it's something that the Irish government are looking at specifically for Dublin. That these low emission zones would ban these diesel vehicles, and also as well from the bus fleet as well, and that's something that the transport authorities in Dublin are trying to change, with trials ongoing at the moment for electric buses, hybrid buses, and also hydrogen buses. Again, these would reduce a lot of the emissions. And research that colleagues of mine within my department in civil engineering, they have looked at this in a more detailed way in relation to the bus emissions by putting sensors on people as they travel, as they walk and cycle and move around our city. So that's it from the presentation. I hope that there are some questions. If anybody has any questions specifically that they don't want to ask now, please feel free to email me, and there's my email address, my Twitter. So if anybody has any questions, I will stop.
Thank you so much, Dr. Caulfield, for your educative presentation. We're sure our audience members have benefited from it. And while talking about the audience members, do you have any questions? Let me start, Dr. Caulfield, with a question. Since you're involved in transportations, is or was your research able to introduce quicker policy change compared with other scientific fields?
One of the things that I've noticed at the moment is mainly because we have to reduce our emissions in transport by so much, and we have to do it so quickly. There is an awful lot of buy-in from government at the moment, and they are listening to the academics. So some of the research that I put out there has gotten into policy circles, and it has been implemented as change around electric vehicles and around the promotion of public transport. So that's happened pretty quickly. The other thing I think as well as scientists, and it's great to be talking to you all today, is that I think COVID has done us a huge favor. And now that, the governments and policymakers are listening to us, they're listening to the science that's coming out, and they know that there are answers there that they can implement. And I think that's one of the benefits. But how we get that policy piece across is something that's very important. And as an editor of transport policy, we always welcome papers around air quality and any policies that can be done to enlighten and change policy across different countries.
Yeah, thanks, Doctor. The pleasure is ours to have you with us today, and we're so happy that the research has impacted also the policies and that it's doing good work out there. Somebody just asked Dr. Caulfield that you please share the link to the research paper.
Yeah, of course, I'll do that now.
Thank you. While Dr. Caulfield shares the link to the research paper, please feel free to ask your questions.
Doctor, thank you for your presentation, and I have a question. Do we know anything about the types of sensors installed in the bicycle?
So the sensor that was installed on, I've just shared the link to the paper. The sensors that were installed on the bicycle were just GPS trackers, and it was just measuring where people were traveling to and from. There was no sensors there taking up air quality measurements. And there's been a lot of research that's been done on this. Our approach was much more of a modeling approach as opposed to working out the emissions from sensors on the bikes. So there is obviously, and it's one of the big caveats in the paper, that better emissions modeling and how you do that would be and how you collect that data is something that further research should be done on. But in the time frame that we had, and also the fact of COVID and safety and all the rest, it was decided to model it and just use this GPS tracking data. I hope that answers your question.
Yeah, interesting, and then that also can be fruitful for further partnerships, maybe with OpenSeneca sensors in the near future. Once again, thanks a lot, Dr. Colfeld, for accepting our invitation and for sharing your research paper with us. And we hope to see you in our upcoming events. Thanks a lot.
Thank you very much. Thank you, everybody.
The pleasure is ours. We'll immediately now move to our second student presentation by Mr. Mansouri Alauddin. Alauddin is a health, safety, and environment engineer at CEDIM Engineering, having taken up the post in 2017. The National Company of Studies and Realization of Industrial Projects, abbreviated SIDM, CEDIM Engineering, is a joint stock company founded in 1969 as the engineering department of the National Steel Company for the realization of transformation and distribution projects of metallurgic products. His current role ensures good operating and working conditions in given professional environments, such as industrial sites or logistic warehouse. He also ensures that the company's activity does not have a negative impact on the environment. That's why today's presentation will be on control of air quality in Oran City, Algeria. Welcome, Mr. Mansouri, and the floor is yours.
Hello, everyone.
Hello, Mr. Mansouri.
Hello.
Let's go ahead.
Yeah, thank you. Hello, everyone. It's clear, the power is clear for all?
Yes, it is.
Okay.
Yeah, it would also be better if you can put it on the presenting mode, so it's bigger.
Yeah, okay. Wait a minute. Hello, everybody. The subject is control of air quality in Oran City, Algeria. So we start. So for the content introduction, the second is the material and the methods. Third is choice of the site, the measures. The fourth is the result and discussion. 5 is conclusion. So we start with the introduction. The atmospheric pollution stands out of the subject today, which worries more and more the citizens, the research and government policies Ministry of Health. In this work, we are discussing mainly about automobile pollution of the city of Oran. The data are recently made in January and February, August and September 2016. We are showing through paragraphs the result of this sample taken of specified and chosen sites around and in the city of Oran, like nuclear plant and Oran roads. You see the material and methods. An assessment of air pollution in different districts of the city at different hours is evaluated given an overview of the air quality. The measures have been taken using a portable device close to car traffic on height 1 meter. The duration of each measurement is 3 minutes, and the result is an average of 3 tries. 7 sites kept for the company of measurement are reposted in the graphical card. The choice of the study area for the 7th site was determined on operational argument and residential area which very high traffic like downtown bus stop. This is the application, the device mobile. Choice of the site, the measurements of pollution. We have 7 sites. The first is Gambetta. The second is Place Victor. The third is Medina Jadida. 4 is Al Sharfawi. 5 is Rompa Al Hamri. 6 is Rompa Esto. And 7 Agid Lotfi. The results and discussion. This is the result obtained in January 2016. The level of average concentration all of the time slots between 11 and 13, and in the evening 16 and 18. In the ambient air in oxide carbon and oxide nitrogen in January. The same work obtained in the February 2016. And also in the summer, the work is result obtained in August 2016. The levels of average concentration of the time slots between 11 and 13 and 16 at 18 in the air ambient oxide carbon and oxide nitrogen in August and also September. Assessment shows that the value of oxide carbon and oxide nitrogen are different depending on the rushing hours, which is normal. Moreover, the values in August and September are higher because it increased the traffic caused by the tourists in the summer. From it, we can say the value of oxide carbon and oxide nitrogen varies according to the season and the rush hours. Also with result and discussion, this is the summary of the most polluted sites. In January, we have Place Victor, Agid Lotfi, for oxide of nitrogen. In the morning, Agid Lotfi. In the evening, Sharfawi. In the February 2016, for the pollutant carbon monoxide, it's Rompa Al Hamri in the morning and Gambetta. In the oxide of nitrogen, in the morning, it's a place Agid Lotfi, and evening Gambetta. In the August, for monoxide carbon, it's Gambetta. In the evening, Medina Jadida. For both oxide of nitrogen, Agid Lotfi in the morning and the evening Gambetta. In the September, the carbon monoxide is Place Victor, Medina Jadida, and for about pollutant nitrogen oxide, it's Gambetta and Agid Lotfi. For the conclusion, this study confirmed the impact of the road traffic, oxide carbon and oxide nitrogen pollution, particularly in the almost place in the city of Oran. We conclude for all that Oran is a city exempt from pollution because everybody can realize from now and nuisance caused by the pollution of the traffic. Graphs indicate increase of the content in NOx during the winter period and a summary, the January and February and August and September. The business resumption of September also leads the increase of the rate of oxide nitrogen. The winter, the weather conditions are more penalizing and the human activity In particular, the road traffic is maximal. The city of Oran has weather conditions that help to disperse pollutant. Yes, that doesn't mean it's not a polluted city, because it can be seen at midday rush hour or weekends that cause difficulty breathing and bad smells. Far from beginning a simple problem, pollution has become increasingly common. And finally, thank you for your listening.
Thank you so much, Mr. Mansouri, for your presentation. We really appreciate it. We would be able to have any questions because we are behind in time. Sorry, but hopefully we'll see you in the upcoming events. Thank you.
Oh, thank you.
And do we have Mr. Saeed Naili? Mr. Saeed Naili? Maybe Mr. Saeed Naili wasn't able to make it today. Therefore, we'll go directly to the concluding remark. So thanks to ReachSci, represented in its president, for such an opportunity to have all those brilliant minds with mutual interests to meet. Thanks to the amazing volunteers who organized the conference in such a short time, and I have the privilege to be leading such a team. And many thanks to our keynote speakers and researchers for their interesting talks and time. Thanks to everyone for being here and being patient. We hope you have learned something new and interesting today. We're planning to have more conferences like these. Thus, your feedback will be important to help us improve our conference and our participants' future experiences. Therefore, please feel free to express your thoughts and give feedback. We have a link in our website to send your feedback about the conference, or otherwise, we will be also sending you the link by emails. Thanks a lot for your time, and well, now we'll be having our network session. Thank you.
Great, everyone. Yeah, thank you for amazing conference. Put really hard work for speakers and people who organize the meeting.